Hello guys, how are you today? So today I'm gonna be explaining the full AP chemistry revision from the CQDs. So please pay attention to which CQD you open, not the AS one, the AP one. So the very first chapter we have is chapter 6 from fundamentals. We only have section 6.1 and they selected a few questions for us. So I'm not gonna be doing any top questions unless they are required from us, but I will try to do all of the grids if I see any and they did not assign them. So the first questions we have, they are from 1 until 7. Let's get started. So section 6.1, the gaseous state. Question 1 grid, it says list the postulates of kinetic molecular theory of ideal gases, okay? Very simply, there is 4 main important things you need to know. I'm gonna say them, okay? But I'm gonna summarize them when I write them. Very simply, the first theory, okay, is that a gas is made of tiny particles of negligible volume compared to the volume of its container, so they are point masses. So basically, we can summarize it into ideal gases have negligible volume. Ideal gases have negligible volume. What do I mean by the sentence that I just said? That a gas is made of tiny particles of negligible volume compared to the volume of its container, so they are point masses. Basically, they're saying that the molecules of ideal gases are super duper tiny compared, of course, to the volume of the container, that they are not even considered to have a volume. So that's why we call them something which is point masses, okay? So that's the first postulate. What's the second postulate? This is very simple, very easy. The particles exert no forces on each other. So no forces exerted on each other. On each other. This means that they do not attract each other and they do not repel each other. Okay, so now we'll move on to the third postulate. What does the third postulate say? The randomly moving particles collide with each other and with the walls of container in perfectly elastic collision. So the particles undergo perfectly elastic collision. This is something you should know from mechanics, okay, since we have the mechanics final before the chemistry one. This collision. Okay, if it's perfectly elastic collision, then it does not lose any kinetic energy. Alright, so this is again something extra to know. And then last but not least, the final postulate is that the average kinetic energy is directly proportional to their absolute temperature, which means their temperature in Kelvin. Okay, so again, I'm gonna repeat them. The first postulate is that ideal gases have negligible volume compared to their container, so we call them point masses. The second one is that ideal gases do not exert any forces on each other. They do not attract, they do not repel. Third one is particles undergo perfectly elastic collision, meaning that they do not lose their kinetic energy and they do not collide with each other. Sorry, they do not coalesce with each other. They do collide with each other, but they don't stick together. They don't coalesce. Okay? And then we have that the average kinetic energy is directly proportional to the temperature. That means the absolute temperature. That means the temperature in Kelvin. Okay? So that's it for question number 1. We'll now move on to question number 2. What does it say? It says some oxygen, okay, at room temperature and 1 atmospheric pressure, so this is pressure 1, was compressed from 400 centimeter cubed, so this was volume 1, to 50 centimeter cubed, this is volume 2. Assuming that the temperature remains constant, calculate the new pressure of the gas. So they want us to find pressure 2. So I'm not gonna go into the direct explanation. Let me explain to you how we derive this equation and how we may solve it. So we know the general equation PV equals nRT. If I move nRT to the other side, I will get PV over nRT is equal to 1. But now let's say this is pressure 1, volume 1 is divided by number of moles 1 over R. R is always the same, and temperature 1. Okay, so it would be equal to, let's say we have now something different. So now it's pressure 2, volume 2, number of moles 2, R, and temperature 2. Now, you keep this general equation in front of you at all times. Okay, this is the general equation you can deal with. What we can do is we can read our given and we can cancel what is constant among both of the samples. So first of all, we have pressure 1, so we have to keep it. We have volume 1, so we have to keep it as well. We have volume 2 as well. And we need to find pressure too. So they didn't mention any change in the number of moles, so number of moles stayed the same. R is always the same, and they didn't say any change in temperature. That means the temperature is the same. So you can erase this, and now you're going to be left with this equation. P1 V1 is equal to P2 V2. So if we want to find P2, that means P2 would be equal to P1 V1 over V2. So it would be pressure 1, which is 1 atmosphere, times volume 1. Now, do you need to change the units? Not really, because if this and this are both in centimeter cubed, they're going to cancel each other out, right? So 1 atmosphere, let me write it with the units. 1 atmosphere times 400 centimeter cubed divided by 50 centimeter cubed. So this and this cancel. So then what would I be left with? I would be left with 8. And what would the unit I have? What would the unit that I should have be? It will be 8 atmospheres, but am I doing it to the correct number of significant figures? Now, usually they should give you the number of significant figures in the answer. Here they didn't mention anything, but I do believe they are mistaken in the answer key, because I have one significant figure here, one significant figure here, and one significant figure here. So when I am dividing and solving, I should have my answer to one significant figure, which is 8 atmospheres, okay? That's it for question 2. We'll move on now to question number 3. Okay, again, I explained to you how we derive the general equation, which is P1 V1 over N1 RT1. It's equal to P2 V2 over N2 RT2, okay? So, now let's see what it says. A sample of oxygen at 25 degrees Celsius, so this is temperature 1, and 1 atmosphere, so this is pressure 1, had a volume of 400 centimeter cubed, so this is volume 1. The gas was cooled to minus 25, so this is temperature 2. Assuming that the pressure remains constant, so there is no change in pressure, calculate the new volume of the gas. They want us to find volume 2. So we go back to our general equation. We see pressure remained constant, so we can cancel it out from both sides, but my volume changed. Number of moles remained constant, R remained constant, so my equation is what? My equation is V1 over T1 is equal to V2 over T2, right? So of course we need to pay attention to these significant figures, and don't forget that you're changing your temperature from degrees Celsius to Kelvin at all times. How do I change to Kelvin? I need to add 273. I also need to add 273 over here. So this turns into 298 Kelvin, and that one will turn into 248 Kelvin. So this is temperature 2, and this is temperature 1 over here. So what's my initial volume? 400 points, so that's 3 significant figures, centimeter cubed, divided by what? Oh wait, before that, let's get the equation. What do we need to find? We need to find volume 2. So you'll move this here. So V1 times temperature 2 over temperature 1 is equal to volume 2. So what's volume 1? It's 400 point centimeter cubed times temperature 2, which is 248 Kelvin, right? So times 248 Kelvin divided by what? Divided by temperature 1, which is 298 Kelvin. So Kelvin and Kelvin cancel. And then on your calculator, if you put 400 times 248 divided by 298 to the correct number of significant figures, which is 3, you will get an answer which is 333 centimeter cubed, okay? So that's it for question number 3. We'll now move on to question number 4. What does it say? Before we start, just get the general equation. P1 V1 over N1 RT1 is equal to P2 V2 over N2 RT2. Okay, so what does it say? 0.50 mole of O2 gas. So this is the number of mole, right? Of O2 gas at a particular temperature and pressure had a volume of 400 centimeter cubed. So this is volume 1. They want to find volume 2 if we change the number of moles to 1. So this is N2. So that's N1, that's N2. And the keyword here is under the same conditions, okay? So let's see. My pressure is constant. They didn't mention any change. We want to find the change in volume, so V1 and V2 stay. My number of moles changed, so I keep them. But R is always constant, and temperature 1 is constant in this case. So what's the equation I'm going to be using? Excuse me. Let me try to go back up again. Okay, here we go. So what's the equation I will be using? The equation I'm using is V1 over N1 is equal to V2 over N2. So I want to find what? I need to find volume 2. So I'll move N2 here. So it would be V1 times N2 over, over N1, okay? and it would give me volume 2. So volume 2, it's equal to what? It's equal to volume 1, which is 400 centimeter cubed, times what? Times my final, N2, which is 1.0 mole, divided by 0.50 mole. Now, the smallest significant figures I have here is 2 significant figures. That means my answer should be to 2 significant figures. So on your calculator, 400 times 1.0 over 0.50, that's gonna be 800. But if I put a point, this is to 3 significant figures, so I cannot deal with this. Instead, I will need to change it to the appropriate number of significant figures. So I will change it to 8.0. This is 2 significant figures times 10 to the power of 2. And what's the unit that I'm gonna have? I'm gonna have centimeter cubed. Okay, that's it for question number 4. We move on to question number 5. What does it say in question number 5? A mass of helium at room temperature is placed in a cylinder fitted with a piston, and the piston is adjusted so that the volume of the gas is 250 milliliters. So this is volume 1, and its pressure is 0.50 atmospheres. So this is pressure 1. If the piston is raised to become 350 milliliters, volume 2, what will the new pressure be? So they want us to find pressure 2 of the gas, assuming the temperature remains constant. So what's the general equation we know? We know P1V1 over N1 RT1. It's equal to P1V1 over, P2V2 over N2 RT2. Okay? So we know what? We know that number of moles is constant, R is always constant, and the temperature is constant. So the equation we're going to be using is P1V1 over, is equal to P2V2. Okay? So that would mean that P1, which is 0.50 atmospheres, times volume 1, which is 250 milliliters. So far, these two, both of them have 2 significant figures. It's equal to what? It's equal to pressure 2 that we need to find times 350 milliliters, which is also 2 significant figures. So divide by 2 significant figures, which is 350. So here it is atmosphere. Here it is milliliter, and here it's milliliter. Milliliter and milliliter cancel. So on your calculator, 0.50 times 250 divided by 350, I got to the correct number of significant figures, which is 0.36 atmospheres. So that's it for question 5. We'll now move on to question 6. What does it say? Okay, so now we'll move on to question number 6. It says, assuming the volume that will be occupied by 0.50 moles, so this is the number of moles 1, of oxygen at 27 degrees Celsius, so this is temperature, okay, and 1 atmosphere, this is the pressure, assuming, they want us to find the volume, sorry, why did I say assume? I think it's calculate, yeah, calculate the volume. If we have number of moles to be 0.50, we have the temperature to be 27, we have the pressure to be 1 atmosphere, assuming ideal behavior. So this is very important, I'll explain why later. And they gave us the value of R. Now, why did we say assuming ideal behavior is important? Because we can use the equation PV equals nRT. If they said not assuming ideal behavior, there's a totally other equation that we learned last year, but we didn't use it. But it's not that necessary for us to know, we just need to know PV equals nRT. So I need to find my volume. My volume would be equal to number of moles times R times T over pressure. So my volume would be equal to the number of moles, which is to 2 significant figures, times R, which is 0.080, which is to 2 significant figures, times the temperature. So it's going to be 27 plus 273, which is 300 Kelvin. Now, 300 Kelvin, initially it was to 2 significant figures. I don't know if this really affects it, because in the answer key it does not seem to affect it. Anyways, we'll move on. The pressure is what? It's to 2 significant figures because 1.0. Anyways, so whatever answer I get, it needs to be to 2 significant figures. So you put it on your calculator, 0.50 times 0.080 times 300 over 1.0 to 2 significant figures, it is 12 liters. Okay, so that's it for question 6. And then the final question for the set of equations that we have for now is calculate the mass of hydrogen gas that will occupy a volume of this much. So this is our volume at 27 degrees Celsius. So this is what? This is the temperature, and 1 atmosphere. So this is a very important equation. They want us to find the mass given the volume, the temperature, and the pressure. So PV equals nRT, but we have an issue. We have pressure and volume, Okay, they didn't specify for us R, so we're gonna assume R is 0.080. Okay, the temperature, we need to change it to Kelvin, so it turns to 300 Kelvin. The volume, we need to change it to the appropriate units. It cannot stay in centimeter cubed. It needs to change to decimeter cubed. So you're going to divide by 1,000 to get 2.5 decimeter cubed. And now here's the important part. They want us to find the mass, but we have number of moles. But we know that number of moles is mass over molar mass. But we are looking to find the mass, not the molar mass. So we could move the molar mass to the other side. So PV molar mass is equal to mass RT, right? So then I want to find what? I want to find the mass, so I'll move RT to the other side. So PVM divided by RT is equal to the mass. So let's find the mass together. Mass is equal to the pressure, which is 1.0 atmospheres, times the volume, which is 2.5 decimeter cubed, times the molar mass of hydrogen gas. Here you have to pay attention, hydrogen gas is H2 gas, not H gas, so it's going to be 2.0 gram per mole, divided by what? Divided by the R, which is 0.080, times the temperature, which is 300. So the temperature in Kelvin doesn't really affect. So you put it on your calculator, and the correct number of significant figures would be 2. So I would get an answer of 0.21 grams. Okay, that's it for question 8. Now the next question question 7. Now the next question we have is question 9, not 8. Okay, what does it say in question 9? The temperature of a fixed mass of gas of volume 100 centimeter cubed. What does this mean? This is volume 1. And fixed mass means that the number of moles is constant. So N1 equals N2. Okay, it was dropped from 127 degrees, so this is temperature 1, to 27 degrees, temperature 2. The pressure changed from, so this is pressure 1, and this is pressure 2, they want the volume. So now we are back to the comparison equation. So P1V1 over N1 RT1 is equal to P2V2 over N2 RT2. So we know that number of moles on R is always constant. So the equation we're using is P1V1 over T1 equals P2V2 over T2, right? So now substitute the values. 2.0 times volume 1, which is 100 centimeter cubed, divided by temperature 1, which is 127 plus 273. So divided by the volume, which is 400, right? Or sorry, no, excuse me, divided by temperature 1, which is 127, plus 273, which is 400 Kelvin. So it would be equal to pressure 2, which is 1.5 atmospheres, times volume 2, which we need to find, divided by temperature 2, which is 27 plus plus 273, which is 300. So then you'll move these to the other side. So 2.0 times 100 times 300 divided by 1.5 times 400, it's gonna be equal to volume 2. So on your calculator, this is 300 divided by 1.5 times 400, I got an answer of 100. And there's a lot of 3 significant figures, but I think it should be to 2 significant figures. So we can't keep it like this. We'll have to change it. So we'll change it to 1.0 times 10 to the power of 2 centimeter cubed. Okay, that's it for question number 9. Now the next question that we have, it is actually question 15. That's in the recommended questions of the CQDs to do. So let's move on to question 15. They want us to calculate the density of CH4 at 100 degrees Celsius and 5 atmospheres. So PV equals nRT, right? And we can split it into mass over molar mass. So PV equals mass over molar mass RT. What happens if I switch the places of volume and molar mass? I get PM equals mass over volume times R times T. Mass over volume is density. Density denoted by rho, or if you want, you can say D. So now we have this new equation, PM equals DRT. So now they want us to find the density. So density would be equal to PM over RT. So what's the pressure? The pressure is 5.0 atmospheres times the molar mass of CH4. It's gonna be 12 plus 4. That's 16. So 16 divided by R. R, they didn't give it to us, so you'll in the answer key they used it as the full value, which is 0.08206. I believe in the exam they will always give you the value. So 0.08206 times the temperature, but it needs to be in Kelvin, so 100 plus 273, that's 373. So you put it on your calculator, and the significant figures we have, the smallest one is 2 significant figures. So our answer should be to 2 significant figures, so it's 2.6. Now, pay attention. In chemistry, we have to use the appropriate units. In chemistry, for mass, it's always in grams, and the volume is usually in liters or meter, liters or decimeter cube. But I always prefer that we stick with liters, so it's gonna be gram per liter, okay? That's it for question 15. Now, the next question set we have is from 22 to 24. So we don't have these. If you want to watch the full video, I have a full video based off of this. So feel free if you want to do all the questions to watch the video. Anyways, we have 22 now. What does it say? We have 22, 23, and 24. Okay, this is actually one of the most important questions, by the way. It comes a lot, okay? In rigid 8.2 liter, this is the volume. Flask contains a mixture of 2.50 mole. This is the number of moles of H2, 0.50 mole of Cl2, and sufficient argon. They didn't give us the number of moles of argon, so that the partial pressure of argon in the flask is how much? Is 2 atmospheres. The temperature is 127 degrees Celsius. They want us to calculate the total pressure in the flask. So the way that I usually do it, I don't think they did it in the answer key. Actually, yeah, they did it in the answer key. I prefer this way because it's very logical, okay? The first thing that we should do to calculate the total pressure in the flask is we should look at our given. They gave us the pressure of argon, but they did not give us the number of moles of argon. What I could do if I had the number of moles of argon is I could find the total mole, like the total number of moles, then I would have found the mole ratio of argon, and then I would have used it to find the total pressure, okay? So how do I find the number of moles of argon? First of all, I need to know the equation, PV equals nRT. What I'm looking for is N, so N is equal to PV over RT. R always stays the same at 0.0, excuse me for this, we don't really care about it, 0.08, okay? 0.080, okay? Or actually they used it as 0.082, okay? Anyways, the volume in a flask is the same volume for all gases. This is something you should remember. The gases, okay, in a flask, they take the entire volume. So the volume of the flask is the volume of every single gas. So 8.2 is the volume of H2, Cl2, and argon. So the volume of argon is how much? It's 8.20 liters. Now the temperature is the same as well for all the gases, which is 127. So you change it to Kelvin. So 127 plus 273, that's going to be 400 Kelvin. And now the pressure. They gave us the partial pressure, which is how much? Which is 2 atmospheres. So you will have 2 times 8.2 divided by 0.082 times 400. You will get that the number of moles of argon is 0.500 moles. Okay, so let me just get rid of this. We now have that the number of moles of argon is 0.500 moles. What we could find is the total number of moles. Total number of moles would be 2.50 plus 0.500 plus 0.500, and you would get an answer of 3.50 mole. Okay, now what can I do with this? Let me find the mole ratio of argon. Or actually, another way we could do this is because we have the total number of moles, we can apply PV equals nRT again. So the P total, it would be equal to what? PV equals nRT, right? So P total, it would be equal to nRT over V. So the number of moles we have is 3.50, or they choose in this exam to use it as 0.082. Times the temperature, which is 127 plus 273, which is 400 Kelvin, divided by the volume, which is 8.2, you would get what? You would get 14.0 atmospheres. So this is the total pressure in a flask, in the flask, which is 14.0. Okay, now on part B, what does it say? It says the mixture in the flask is ignited by a spark, and the reaction represented below occurs until one of the reactants is entirely consumed. Give the mole fraction of all species in the flask at the end of the reaction. So here we need to first of all find our limiting reagent. Let's take the number of moles. We have 2.50 moles, 0.500 moles in our reactants. Argon does not react, but you should keep in mind that it has 0.500 moles. It contributes to the total number of moles. So looking at our given, we have 2.50 moles of H2, 0.500 moles of Cl2. If we did the limiting reagent ratio, okay, for H2, first of all, it's going to be 2.50 divided by 1, which is 2.50. For Cl2, it's going to be 0.50 divided by 1, which is also 0.50. So for sure, Cl2 has the smallest ratio. That means it is the limiting reagent. That means Cl2, we would use it completely. So in the end, okay, if we had initially 0.500 moles of Cl2, then we will consume 0.500 moles of Cl2, right? Now, what about H2? I had initially 2.50 moles of H2, but okay, we know that the limiting reagent ratio, it's 0.500. And what's the coefficient of H2? It's 1. So I'll multiply 0.500 by 1. It will stay 0.500. So what am I going to do? I'm going to do 2.50 minus 0.500, which will give me 2.00 mole. So I consumed from H2 gas 0.500 mole. Now, we come over here to my reactants. To my products. Initially, it had 0 moles. But its coefficient is 2, so 2 times the limiting reagent ratio, which is 0.500, it will turn into 1. That means I will produce 1.00 mole of HCl gas. Now, something important to not forget is that we also have argon. Argon just does not react, and it has 0.500 moles, okay? So let's calculate the limiting reagent, what is it that they want? They want the mole fraction. So let's calculate the mole fraction for all species. Let's start with H2. First of all, the total number of moles is 2 plus 1 plus 0.500, so 3.50 moles. Anyways, we start with number of moles, Xn of H2, the mole ratio of H2. It's going to be 2 divided by 3.50, so that's going to be 0.571. Now, Xn of HCl, it's going to be 1 divided by 3.50, which is 0.286. And then Xn of argon, it's going to be what? It's going to be 0.500 divided by 3.50. So 0.500 divided by 3.50, that would give me an answer of 0.143. And then last but not least, X of N of Cl2. Because it's fully consumed, 0 over 3.50, that's going to give me 0 in all cases. But in general, because it's consumed, it's going to have a mole fraction of 0. So that's it for question 22. We'll move on to question 23. What does it say? Okay, question 23 is also important because it comes a lot. I think this comes as written, as in not written like typing, you know what I mean? So we'll move on to a 20.0 milliliter. This is the volume sample of neon gas was collected over water. Now this is very important. Over water at 27 degrees Celsius. This is the temperature. The pressure in the tube was 1.32 atmospheres. Now, this is the total pressure. Assume that the vapor pressure of water at 27 degrees Celsius is 25 millimeters of mercury. How do I find the pressure in atmospheres? Whenever I'm dealing with millimeters of mercury, you need to divide by 760. So 25.0 millimeters of mercury divided by 760 millimeters of mercury, I got an answer of 0.0329 atmospheres. Of course, to the correct number of significant figures, which is 3 significant figures. Okay, so the absolute temperature in Kelvin is 27 plus 273, which is 300 point Kelvin. Now, the pressure in the tube, the total pressure, it's equal to the water vapor, so pressure of water, in addition to the pressure of neon. So 1.32, it's equal to pressure of water plus 0.0329. Move this to the other side. And I got that the pressure of water, it's 1.29 atmospheres. Now, what do they want? They want us to find, excuse me, my bad. The pressure of neon is what we didn't find. This is the pressure of water. My bad. This is the pressure of neon. Excuse me. So the total pressure is pressure of water plus pressure of neon. Pressure of neon, pressure of water, we found it to be 0.0329. So we need to find pressure of neon. Pressure of neon is 1.29 atmospheres. So now they want us to find the number of moles of neon gas collected. So here we can use PV equals nRT. So we need to find the number of moles. So number of moles is equal to PV over RT. What is the pressure? The pressure, we found it to be 1.29 atmospheres times the volume, which is 20 milliliters. But we can't keep it in milliliters. We need to change it into liters, so we divide it by 1,000. So 20 divided by 1,000. Okay, divided by R. They didn't give us R, but we'll assume to use the full value, which is 0.08206 times the absolute temperature, which is 300 point. So we should have a minimum of 3 decimal places, because 3 Here we don't really care about it because we're changing it, and then 3 as well. So we should have only 3 decimal places. So the number of moles that we will get is 1.05 times 10 to the power of minus 3 mole. Okay, so that's it for question 23. So now we'll move on to question 24. What does it say? When do real gases behave most ideally? Most ideally means what? Means it follows the rules that we talked about, which was the very first question. That means they exert no or minimal force on each other, and they occupy what? They occupy less volume. Okay? Now, this is usually the case in real gases when we're dealing with the lightest gas. First of all, they need to be light. For example, H2 gas is more ideal than O2 gas because it's lighter than O2 gas. Then it should have a higher temperature. That means a gas at 300 Kelvin is more ideal than a gas at 200 Kelvin. Then it should have low pressure. Now let me explain why in each case. So let's go back to the first set of rules that we wrote, okay? Or like the, I forgot what they were called. The rules, okay? Or the assumptions of ideal gases, okay? Why, if they are lighter, they will have a more ideal behavior? Very simply, because they have what? If they are lighter, then they are smaller, right? They have small atoms or molecules, so they have negligible volume. On top of that, they have weaker intermolecular forces, right? And we know that they exert no forces on each other, and they're smaller. That means they have a less volume. Now, why does a high temperature make the gases behave more ideally? Very simply, because at high temperature, there's fast motion, right? So molecules have a much faster motion. On top of that, because they have a fast motion, you will know that their kinetic energy becomes much larger than the attractive potential energy. So thus, they are going to exert minimal, so no, or in some cases minimal, because it's a real gas, okay, force of attraction on each other. All right, now, why? What about the low pressure? Very simply, if we decrease the pressure, okay, that means our volume needs to increase. If our volume increases, then the gas will occupy a larger volume, so the molecules are farther apart. When the molecules or the particles are farther apart, the intermolecular attractions are negligible. The actual size of the molecules are then tiny compared with the total volume of the container. So thus, this is why real gases behave most ideally when it's the lightest, when it has highest temperature, and when it has the lowest pressure. Now, in the exam, what they usually do is they flip it. They say, when do real gases behave the least ideally? So they must be the heaviest, right? They must have the lowest temperature, and they must have the highest pressure. Okay, that's it for question 24. Now, the last question we have, we don't have 25, we don't have 26, but we do have question 29, this question over here. 5 gases, okay, 5 identical balloons under the same conditions, that means same temperature, same pressure, same number of moles, okay, each contain the following gases. They contain C2H6, which has a molar mass of, so C2H6 has a molar mass of 30, SO2 has 64, O2 is 32, CO is 28, and neon is also 28, okay? They said which balloon contains the greatest mass of gas because they have the same number of mole, the same pressure, the same volume. Okay, the most important factor is that they all have the same number of mole. They have the same number of mole. That means that the heaviest gas, which is SO2, would have the greatest mass of gas. So, very simply, SO2, the answer is SO2. When they say explain, you just need to say this. Using Avogadro's hypothesis, equal volumes of gases kept under the same conditions contain equal number of moles. This is true. That's what Avogadro discovered. So SO2 will have what? Will have the greatest molar mass, therefore the greatest mass. Okay? Now compare the average kinetic energies of the gas molecules in balloons because they're all under the same temperature, and we know that the average kinetic energy is directly proportional to the absolute temperature. You will say they all have the same kinetic energy because they are all at the same temperature. Okay? Now, which gas is expected to deviate the most? Now, not which gas is most ideal? Deviate, pay attention, deviate the most, that is least ideal. The keywords are the words in the sentence. So the heaviest gas is usually the one that would deviate the most. So why? They're saying very simply SO2 because it has the largest molecules and the largest electron cloud size. So its particles occupy the largest space and have the strongest intermolecular forces between them. Now, 6 hours after being filled, all balloons have decreased in size. Predict which balloon will be the smallest and explain. So here we need to use a very famous equation. The speed of the lighter gas over the speed of the heavier gas. We're not going to use it, but just I need you to know it in case it comes in the exam. Over the speed of the heavier gas, it's equal to what? It's equal to radical, the molar mass of the heavier gas, divided by the molar mass of the lighter gas. Okay, keep this equation in mind because they might ask you, even though they didn't tell us in the required question. But basically what it's saying is that the lighter the gas is, the greater its speed is. So we need to look for the lightest gas. By the way, excuse me, I did the calculation mistake. Neon is 20, not 28. Okay, so by the way, it wasn't like a calculation mistake. It's just because I have my periodic table above me. So I looked and I wasn't really wearing my glasses, so I couldn't see. So I read it as 28, okay? So anyways, we will see that the lightest gas is neon, okay? So because neon is the lightest gas, okay, it will have the fastest effusion rate. So it will effuse the fastest out of the balloon, and thus the size of the balloon that contains neon will become the smallest. So that's it for chapter 6 fundamentals and 6.1. We only have 6.1, by the way. Whatever else we don't have. So all of this, we don't have it. Okay? So that's it for this video. Thank you guys for watching, and we'll see you in the next chapter. Hello guys, how are you today? I hope that everyone is doing well. So today in this part of the video, I'm going to be explaining the required questions from Chemistry 1, Interactions and Compound. Please pay attention. It's Interactions and Compounds part 1, not part 2. Okay, so for chapter 1, so actually in Interactions and Compounds, we have chapter 1, 3, 4, and 5, and that's it. For chapter 1, we have only 4 questions. So they are questions 7, 16, 17, and 20. So without further ado, let me get started with the first question, which is question 7. Okay, let's read the given. 100 centimeter cubed of 1 molarity HCl aqueous was mixed with 100 centimeter cubed of 1 molarity NaOH aqueous at 20.10 degrees Celsius in a coffee cup calorimeter. The maximum temperature recorded due to the reaction was 26.10 degrees Celsius. Calculate delta H for the reaction. Now, delta H, you should know, it's equal to what? It's equal to minus Q over N. So basically, in order to find delta H, I need to find Q and I need to find N. Now, how do I find Q? Very simply, I look at the unit of my specific heat, right? I have specific heat capacity. Let's look at my unit. I have joules, I have degrees Celsius, and I have gram. So joules, Q, it's in joules, okay? I have C, my specific heat capacity. This is all you have to think about the units and how to solve. Grams is in what? Grams is in mass, and degrees Celsius is what is the change in temperature. So I will use this equation, Q equals mc delta T, to find the value of Q. Now what about the number of moles? This is a very important factor. So here the number of moles, we can find it using stoichiometry. So they actually gave us the equation over here, which is H plus OH minus will give us H2O. So let's find the number of moles. Here my number of moles is going to be 0.1 times 1. Here my number of moles is going to be 0.1 times 1. How did I know? Because I have my volume, I have my concentration. I have my volume, I have my concentration. I need to change my volume to the proper units. I can't keep it in centimeter cubed, so I change it to decimeter cubed by dividing by 1,000. So I'll get 0.1 times 1 and 0.1 times 1. Now we need to look for the limiting reagent. So you do the limiting reagent ratio. You will get that the ratio of H plus, it's equal to 0.1 because it's the number of moles divided by the coefficient, and the ratio of OH minus, it's equal to what? It's equal to 0.1 as well. So because they both have the same ratio, there is no limiting reagent, the equation goes to completion, or the reaction goes to completion. So now using stoichiometry, I could use either one. I can say that 1 went to 0.1, 1 went to 0.1. So the 1 the coefficient 1 of the H2O will turn into 0.1 moles. So what's the number of moles of H2O? It is 0.1. Now, of course, to the correct significant figures, this would be 100, right? So it would be 0.100 moles, okay? Now, let's solve for Q. Q, we said it's MC delta T. What is the mass? Here they gave us something very important. They said the density of the solution is 1 gram per centimeter cubed. So I have 100 centimeter cubed. Then I mix it with another 100 centimeter cubed. So my total volume, it's how much? It's 200 centimeter cubed, right? So this is my total volume. I will multiply it by my density, which is 1 gram per centimeter cubed, to get what? To get the mass. I got my mass to be 200 grams. So I have my mass now, which is 200 grams. So it's 200 times the specific heat capacity, which is 4.2, times the change in temperature. Now, the change in temperature does not matter if it's in degrees Celsius or in Fahrenheit, because it's just the change. The change will be the same value, whether it's in degrees Celsius or in Fahrenheit. So what's the final temperature? 26.10 minus the initial temperature, which is 20.10. You will subtract them, you will get 6 as the difference. Yeah, so times 6.00. And this is 4.20, and this is 200 point. So now, what are you going to do? You will find the value of Q. So it's going to be what? It's going to be 200 times 4.20 times 6.00. I got an answer, which is what? Which is 5040 joules. But there's something very important you need to pay attention to. When we are finding delta H, I need my Q to not be in joules, it needs to be in kilojoules. So I will divide by 1000 to get my answer in kilojoules. So I will get 5.04 kilojoules. Perfect, that's amazing. Now to find the value of delta H, it's going to be minus Q, which is minus 5.04 divided by N, which is 0.100. So you put it on the calculator and to 3 significant figures, my answer will be minus 50.4 kilojoules per mole of reaction, because this is per 1 mole of the reaction. So that is it for question number 7. We found the delta H of the reaction by using a set of equations and by finding it, okay? So now the next grid we have is question number 16. So we're skipping all of these and going to question 16. What does it say? It says calculate the standard enthalpy change for the following reaction in kilojoules per mole, given that the following values, okay, they want us to find the standard enthalpy change. So again, let's repeat the question. What do they need? Calculate the standard enthalpy change for the following reaction in the kilojoule per mole. So whenever they ask you for the standard enthalpy change, mainly of formation, and they give you the enthalpy change, the enthalpies of formation, which is the case, they gave us the enthalpies of formation, then we would use this equation that delta H, it's equal to what? It's equal to the sum of the heat of formation of products minus the sum of the heat of formation of reactant. So the most common example in which we do reactants minus products is if they give us the bond energies. That means they give you the energy of every single bond. Here they did not give us the energy of every single bond. They gave us the delta H of formation. They gave us the heat of formation of the things that are formed. Now you will notice for elements alone, such as oxygen, there is no heat of formation because oxygen exists in nature. It cannot be created, it cannot be destroyed, right? So that's why it does not have a delta H of formation. So anyways, what we need to do, they want us to find the standard enthalpy change. So we'll need to follow this one. Why? Because they gave us the heat of formation. So delta H, it's going to be equal to what? It's going to be equal to the sum of the heat of formation of the products. So that's going to be here. This is our product. So 16 times the heat of formation of carbon dioxide, which is minus 394, plus, open brackets if you want, plus 18 times the heat of formation of water, which is minus 286, okay, all of it is subtracted from the sum of heat of formation of the reactants, which is what? Which is 2 times the heat of formation of C8H18, which is minus 269. So you put it on your calculator and please put the exact bracket. So 16 times minus 394 plus 18 times minus 286, all of it minus 2 times minus 269. So once you put it on your calculator, to the correct number of significant figures, here the significant figures are all three significant figures. So your answer should be to 3 significant figures. So my final answer, it's going to be what? It's going to be that delta H is equal to minus 1,0900 kilojoules per mole, which is exactly what? Which is exactly to 3 significant figures. So we finished from question number 16. Now we'll move on to question 17. What does it say? It says, use Hess's law to calculate delta H for the reaction. So this is the final reaction that we need to end up with, and these are like parts of the process that they gave us. So what I like to do is I like to separate each thing by its own, and then we solve each thing by itself, right? We start with the very first important part, which is 2Fe2O3 in the reactant side. Where do I find Fe2O3? Here. But I have an issue. It's in the product side. So to change it from the product to the reactant side, I need to multiply it by -1. But then I have another issue. This is 2Fe2O3 and this is 1. So what do? I also multiply this by 2. So I multiply it in total by -2. Am I done yet? No, but let's proceed with what we did. So it turns into 2Fe2O3 gives me 4Fe plus 3O2. Okay? Now, the next step that I need to do is I need to change my carbon from 1 carbon into 3 carbon, and it needs to be on the product side. As you can see, it's already on the product side, so I just multiply this by 3. So I'll end up with 3 carbon plus 3O2 will give me 3CO2. So look, this and this are on opposite sides, so they subtract. 3 minus 3 is 0, so this disappears and this disappears. And so my final result would be what? My final result would be 3 carbon plus 2Fe2O3. Okay, it gives me what? It gives me 4Fe plus 3CO2, and this is exactly what they have over here. So now let us find the delta H of the reaction. Delta H, it's equal to what? It's equal to minus 390 times 3 plus minus 820 times minus 2. So, I got an answer to the correct number of significant figures. So this is point 3 significant figures it should be. I got an answer of plus 470 kilojoules. Please remember in the exam to put your plus and minus. That's it for question 17. And now finally, last but not least, the last question that is required, which is question number 20, which is using the bond energies and the enthalpy change. Now, remember, when they give you bond energies and they ask you to find delta H, it's gonna be the bonds broken, which is the reactants, minus the bonds formed, which is the product. So the delta H over here, it would be what? It would be the bonds broken by the reactants minus the bonds formed by the products. So let's see, our reactants are N2 and 3H2, and our product is 2NH3. Now it's important you care about the coefficient, okay? But first of all, let's start by drawing what we see so that we'll not make any mistakes. It's very essential that you draw. So we have N2, N triple bond N plus 3H2. What does it mean? That means you have H single bond H, but it's 3 times. It will give me what? It will give me 2 NH3. Now here, this is why I asked to draw. So you will see we have 3 NH bonds, right? And of course, don't forget about the lone pair. It's not really important to put the lone pair. No one really cares about it when you're solving like this because they don't see your paper, okay? So anyways, we need to look at the bonds only, okay? And we need to find the bonds broken. Let's start with the reactants. We have in the reactants 2 types. We have N2 and we have H2. So N triple bond N, to break it, it needs a bond energy of 941, or it has a bond energy of 941. Okay, now we will add the 2. We have 3 times H single bond H. So 3 times the bond energy of H single bond H, which is 432, right? Now this answer, what am I going to do? I'm going to subtract it by, or subtract it from the bonds. Or actually, no, subtract it by, not from. Very important. From means I'm talking like I'm taking it away from something. No, I'm taking something away from it. So I'm going to subtract it by what? By 2, right? Times. Now, how many NH3 bonds do I have? I have 1, 2, 3 NH3 bonds, right? So that's going to be 2 times 3. So 2 times 3 times, what's the bond energy of NH? It's 391. So on your calculator, you can put 941 plus 3 times 432, all of it minus 2 times 3 times 391. So put it on your calculator. I got an answer, a final answer to the correct significant figures, which is 3, to be minus 109 kilojoules per mole of reaction. It's very important. Okay, so that's it for this video. These are the required questions. I'm not gonna do any more than this because I have already solved all of the these CQDs previously, you could check them out in my other video, okay? So now, thank you guys for watching. I'll see you in the chapter 3. Hello guys, how are you? And welcome back to chapter 3 of AP Chemistry Full Revision. So again, I'm only gonna be doing the required questions, okay? This is for part A, by the way, revision. If you want the full chapter, I have done a separate video on it, so you could check it out if you would like. So let's move on with chapter 3. Chapter 3, we have sections 3.2 and 3.3. We have questions 3 till 9 and then 11 till 20. So let's get started with question 3. Calculate the value of K for the following two reactions. When they say K, they mean K equilibrium. Or actually not K equilibrium, just K in general. Now, K, you should know it's equal to what? It's equal to concentration of products to the power of their coefficient divided by concentration of reactants to the power of their coefficient. But here we have a problem. We don't have any values. However, we have a basis to work off from, which is here, and they gave us a value of K. As you can see, all of the equations are similar, except one thing, that they are multiplied by something different. For example, I went from 2SO2 plus O2 to 2SO3. It took me to SO2 plus half O2, gives me an equilibrium SO3, so I multiplied this whole equation by half, right? And then, same here, I went from 2 to 4, from 1 to 2, and from 2 to 4 again, so I multiplied all of this by 2. But now, this is something very important. Whatever I multiply my equation by, I will put it as an exponent to my original expression in K, of course, if they are the same equation, just the difference is the coefficient. Okay, so here my K prime, it would be equal to 2 to the power of half. Why? Because I multiplied it by half. And then here my K double prime, it would be 2 to the power of 2. Why? Because I multiplied it by 2. So here I would get radical 2, which is 1.4. And here I would get 4. And that's the value of K, very simply, for question 3. We'll now move on to question 4. What does it say? So now we'll move on to question number 4. What does it say? Write the equilibrium constant expression and specify its unit. So you should know that the equilibrium constant, it's the concentration. Sometimes concentration, actually it is concentration, unless they want the equilibrium or the pressure constant, okay? Then you would have to define with the partial pressure, okay? Anyways, here it's the concentration of products to the power of their coefficient divided by the concentration of reactants to the power of their coefficient. Now, something you should pay attention to is that these states need to be either aqueous or gaseous. Either aqueous or gaseous, nothing else. So, for the first one here, it would be what? Kc, which is the equilibrium constant, it's equal to what? It's equal to the concentration of the product, which is N2O4, and it's a gas, so it will work, to the power of its coefficient, which is 1, divided by the concentration of NO2, which is a gas, so it also works, to the power of its coefficient, which is 2. Now, imagine this does not exist, and it's just m over m squared. So then this m and m cancel, and I'm left with 1 over m, and I could substitute m with mole per decimeter cubed. So 1 divided by mole per decimeter cubed will give me decimeter cubed per mole, okay? And that's it for part A. We'll now move on to part B. For part B, it's gonna be what? It's gonna be the Kc, it's equal to the concentration of CH3OH to the power of 1 divided by the concentration of H2 squared times the concentration of CO. So basically, it's m over m squared times m. So m and m cancel. So now I have 1 over m squared. So 1 over mole per decimeter cubed squared. So that's going to be what? That's going to be decimeter to the power of 6 divided by mole squared, okay? So that's it for part B. Now we'll move on to part C. What does it say in part C? Part C, it's very simply Kc is equal to the concentration of H2O to the power of 4. Now here you don't put it because it's a solid, divided by the concentration of H2 to the power of 4, and here you don't put it because it's a solid. So anyways, you have m to the power of 4 divided by m to the power of 4. They cancel, so you have no unit. It's unitless, okay? So that's it for question number 4. We'll move on to question number 5. What does it say? In question number 5, it says, write the equilibrium expression for each of the following reactions and give its type where applicable. So let's start. I'm gonna do A, B, C, D, and E, but before I start, let's just take a quick look over it. I have gas and gas, so I could either talk about Kc or Kp. One is concentration-wise, one is pressure-wise, okay? Here I have aqueous and liquid, so the only thing I can talk about is Kw, but pay attention. I have H2O, which is water, so I could say that it's the equilibrium expression of water, or the dissociation of water. Now, for the other one, look what I have. I have an acid. It will dissociate into the H plus and the OH minus. This is Ka, the dissociation of an acid. Here I have a base. I add to it water, and it dissociates into the NH4 plus and the OH minus. So this is Kb, the dissociation of a base. And here I have AgCl solid. It will give me Ag plus and Cl minus aqueous. So this, we call it Ksp, which is the solubility product constant, okay? So for part A, let's find Kc and Kp. Kc here, it would be equal to concentration of CO, okay? Divided by the concentration of O2, to the power of half. Here we don't include it because it's a solid. There's no need to put the units because it didn't ask us for the units. Or we could find Kp. Kp is going to be the partial pressure of carbon monoxide divided by the partial pressure of oxygen gas to the power of half. Either work, okay? Now for Kw, it's going to be what? It's going to be the concentration of product, so H minus times concentration of H plus, divided by the concentration of reactants. Because it's a liquid, we cannot include it, so instead of it, we will put 1. So divided by 1, so it's going to be concentration of OH minus times concentration of H plus. Now, we have Ka. Again, we need to do concentration, the acid constant. It's going to be what? It's going to be concentration of CH3COO minus times the concentration of H plus divided by the concentration of CH3COOH. That's it. Now, the Kb, the constant for the base, it's going to be what? It's going to be the concentration of OH minus times the concentration of NH4 plus divided by, you don't include water because it's a liquid, so divided by the concentration of NH3, which is aqueous. So yeah, that's pretty much it. And now last but not least, the solubility product constant, it's gonna be concentration of Ag plus times the concentration of Cl minus divided by 1. Why? Because this is a solid. And that's it for question number 5. We will now move on to question number 6. What does it say? It's saying, write the equilibrium constant expression in terms of partial pressure and determine its units. So Kp would be equal to the partial pressure of Cl2, right? To the power of the coefficient, which is 1, times the partial pressure of PCl3, to the power of its coefficient, which is 1, divided by the partial pressure of PCl5. Now they want its unit. So imagine this is pressure times pressure over pressure. Pressure and pressure cancel. So what's the unit of pressure? It's Pascal. When you're dealing with chapter 3, the unit of pressure is Pascal and not atmospheres. Please pay attention. Now let's move on to part B. It says the partial pressures of PCl5 and PCl3 at equilibrium at temperature T are 3 times 10 to the power of 4 Pascal and 2.7 times 10 to the power of 4 Pascal respectively. They said determine the equilibrium partial pressure of Cl2 if the total equilibrium pressure is 1.54 times 10 to the 5 Pascal. So they gave us what? They gave us the total equilibrium pressure, they gave us the partial pressure of PCl5 and the partial pressure of PCl3. They want us to find the partial pressure of Cl2 gas. So very simply, the partial pressure of Cl2 gas is equal to the total pressure minus the partial pressure of PCl5. Please put your brackets, it's very important, plus the partial pressure of PCl3 and then close your bracket. So then on your calculator, 1.54 times 10 to the power of 5 minus what? Minus the partial pressure of PCl5, which they gave it to us as 3.0 times 10 to the 4, plus the partial pressure of 2.7 times 10 to the 4. Close your bracket, and I got an answer. They wanted to, how many significant figures? To 3 significant figures? No, actually, look, 3 and 2. So they wanted to 2 significant figures. So I'm going to change my answer to 2 significant figures. So I can say it's 97 times 10 to the power of 3, or I could say it's 9.7 times 10 to the power of 4 Pascal. So that's it for question 6, part B. Now we'll move on to question 7. What does it say? So question number 7, let's see what it says. A sample containing 6 moles, so this is the number of moles of each H2 gas and I2 gas were introduced into a 3 decimeter cubed vessel. So what would my concentration be? It would be the number of moles divided by the volume, so 6 divided by 3, which is 2.00 molarity, okay? Now, at a temperature T where the following reaction occurred, the reaction has an equilibrium constant K of 25. Calculate the equilibrium concentration of all gases. So here we need to do the ice table. So let's rewrite the equation. So H2 gas plus I2 in equilibrium with 2HI. Please don't forget the states. I'm only doing this because I already know all of the states of whatever we're dealing with. Okay, so ICE, right? So we need to do the ice table, okay? First of all, we start with the initial concentration of H2 and I2, which is the reactants. They gave it to us, which is 2.00 molar. 2.00 molar. And then the initial concentration of HI, it's 0 because they didn't tell us anything, so we're gonna say that it's 0, right? Then, anyways, we have a change. What happens? Because there is an equilibrium constant, right? First of all, we need to check the value of Q. What's the value of Q? The value of Q is going to be the concentration of products, which is 0, divided by the concentration of reactants, which is 2 squared, so I'm going to end up with a 0. Since Q is less than K, then my forward reaction takes place, so my reaction will move like this. That means this would decrease by X, this would decrease by X. Why did I say X? Because you look at the coefficient and you multiply X by it. And here, because it's on the product side, it's going to increase by 2X, okay? So I end up with what? I end up with 2 minus X, 2 minus X, and plus 2X. So now I should know that the K, this is an equilibrium. It's going to be what? It's going to be 2X over 2 minus X. Oh, wait, here's something important. 2X squared. Why? Because it's the concentration of HI to the power of the coefficient, which is 2, divided by the concentration of H2 and I2, which is 2 minus X, and times 2 minus X again. So instead of writing it twice, I can just square it. It's equal to what? It's equal to 25. So now what I could do radical here and radical here. So then I'll end up with what? I'll end up with 2x over 2 minus x is equal to 5. Always take the positive value, okay? So you move 2 minus x to the other side. I got 2x is equal to what? It's equal to 10 minus 5x. I'll move this to the other side. 7x is then equal to 10. So then x is equal to what? It's equal to 10 over 7. But this is not what I need. They want the equilibrium concentration of all gases. So the concentration of H2, it's going to be what? It's going to be 2 minus x, so 2 minus 10 over 7. Okay? And it's also the same as the concentration as of I2. And then the concentration of HI, it's going to be what? It's going to be 2 times 10 over 7. So here, what will I get as an answer? Here, 2 minus 10 over 7, I got as an answer 0.57 molarity. And here, 2 times 10 divided by 7, I got as an answer 2.86 molarity, okay? So that is it for question number 7. We'll now move on to question number 8. What does it say? Let's read what it says. In ester ethyl ethanoate, okay, it undergoes hydrolysis under certain conditions as shown below. A sample of 0.500 moles of ethyl ethanoate is added to 0.500 moles of water in the presence of catalyst to form 500 centimeter cubed solution and an inert solvent. So first of all, we can find the number of moles. How do we find the number of moles? It's gonna be we can find the concentration, Concentration is number of moles divided by the volume. The number of moles, it's gonna be 0.500 divided by the volume, which you need to change to the appropriate unit. So 500 divided by 1,000, that's 0.5. So 0.5 divided by 0.5, my concentration is 1 molar. Okay? So then what do they say? This is, by the way, the concentration for both ethyl ethanoate and water, okay? Then what do they say? They say at equilibrium, 0.175 mole of ethyl ethanoate are present. So the concentration is going to be 0.175. Excuse me, let me return this to the original position it was in. I think it was like this. Can't really play with it. It's okay. So it's going to be the number of moles of ethyl ethanoate, which is 0.175, divided by the volume to the correct unit, which is 0.500. So 0.175 divided by 0.500, I got 0.35 molar, okay? So now here we can do the ice table. So let's put the format of the ice table. Please excuse the writing, but because I don't have any space to do it. So ICE, okay? Let me choose a nicer color that it's visible. So here initially I had 1 molar. Actually, this is not clear. Let me use green. Here I had 1 molar. For water, because it's a liquid, I can't take its concentration. CH3COH, I can't take its concentration. Or no, actually, what am I doing? Excuse me. This is a liquid, and this is a liquid, and this is a liquid. Okay. In a case like this, when we have a homogeneous solution, what does a homogeneous solution mean? That means all my reactants and products are all the same state. Then, even if it's liquid or if it's solid or if it does not have a concentration that we can like turn into, like we cannot use its concentration, then we can use it if it's a homogeneous solution. So usually, if you have water, you're going to leave it blank. But in this case, because I have a homogeneous solution, what I can do is I can use the values of their concentration. So here, this is going to be 1 molarity. 1 molarity. Here, CH3COH, it's 0, 0. What happens now? Might change. Here, because the forward reaction takes place, how did I know? Because I have 0 concentration initially in my product, so of course the forward reaction is going to take place. Okay, so what's going to happen? I'm going to lose x, right? And I multiplied by the coefficient, which is 1, so minus x. Here, minus x. Here, plus x. Here, plus x. So do you get? I either lose or gain x, and then I multiplied by the coefficient of what I'm dealing with. So they told me that the concentration, the equilibrium concentration of ethyl ethanoate, it was what, 0.35. So I can now find the value of x. I know 1 minus x, it's equal to 0.35. So x is going to be equal to 0.65. So here it's also going to be 0.35, here it's going to be 0.65, and here it's going to be 0.65 as well. Why? Because x is what, 0.65. But is this to the correct significant figures? No, I did not use the proper significant figures, that's why I won't get the correct answer. But look here, 3 significant, 3 significant, 3 significant, so my answer should be to 3 significant figures. That means the concentration of CH3COOC2H5, it's equal to the concentration of H2O, which is what? Which is 0.350 molarity. But then the concentration of CH3COOH, it's equal to the concentration of C2H5OH, which is what? Which is 0.650 molarity, okay? That's it for part A. Now for part B, they want the value of the equilibrium constant expression. So here, in this case, again, because it's a homogeneous, we can find the equilibrium constant. So here it's going to be the concentration of CH2H5OH to the power of its coefficient times the concentration of CH3COOH divided by the concentration of the reactants, which is CH3COOC2H, C2H5, times the concentration of water. Here, this only works because it's a homogeneous solution, okay? Now, substitute your values. So, Kc, it will be equal to what? It will be equal to 0.65 times 0.65, so 0.65 squared, divided by 0.35, or like 0.650, divided by 0.350 times 0.350 squared, right? So, 0.650 squared divided by 0.350 squared. Put it on the calculator. I got my answer to be 3.45, which is the correct answer, okay? I'm sorry for the mess. I do hope you can see my solving, but because I don't have any space and I need the question in front of me. So that's it for question number 8. We'll now move on to question number 9. What does it say in question number 9? A sample, okay, containing 2 moles of H2, okay, 2 moles of I2 and 10 moles of HI were introduced into a 2 decimeter cubed vessel. So let's do the table of the ice table. 1, 2, 3. So I, C, E. What's the question? The question says, if the reaction has an equilibrium constant Kc equal to 10, is the system above at equilibrium? If not, then calculate the concentration of all species at equilibrium. So let us see, is my system at equilibrium? How would I figure it out? Very simply, I need to find Q. How do I find Q? I need to use my initial concentrations, right? So here I have 2 moles divided by 2 decimeter cubed. This is 1 molarity. 2 divided by 2, 1 molarity. And then 10 divided by 2, that's 5 molarity, right? So Q, it's going to be equal to the concentration of product to the power of their coefficient divided by the concentration of reactant to the power of their coefficient, so 1 times 1. So basically, I got Q to be 25. Since my Q is greater than Kc equilibrium, then my backward reaction is favored. If my Q is less than Kc, then my forward reaction is favored. If my Q is equal to Kc, then it's what? It is in equilibrium. Okay? So here now my backward reaction is favored, so I'm going to be losing from the products and gaining from the reactants. So here 1 times x, so x, 1 times x, so x, 2 times x, so minus 2x, right? So I'll end up with 5 minus 2x, and then 1 plus x, right? So then, now here, what's Kc? Kc, it's 10. And it's equal to the concentration of products, which is HI. Always take the reaction in the form that they gave you. Do not flip it, even if it's the backward reaction. You're taking it like this, okay? So it's going to be the concentration of HI, which is 5 minus 2x to the power of its coefficient, which is 2, divided by the concentration of H2 times the concentration of I2, so 1 plus x squared, because it's 1 plus x times 1 plus x, it's equal to 10. So you can do radical here and radical here. I got 3.16 is equal to 5 minus 2x divided by 1 plus x. So then I'll put it here. I will get 3.16 plus 3.16x is equal to 5 minus 2x. So then you switch places here and here. Okay, so what will you get? 2 plus 3.16, that's 5.16. 5.16x is equal to 5 minus 3.16. What's 5 minus 3.16? 1.84. So x, it's equal to what? It's equal to 1.84 divided by 5.16. I got an answer of 0.357 molarity. So this is the value of x. So now they want us to find what? They want us to find the concentration of all species at equilibrium. So the concentration of H2 is equal to the concentration of I2, which is what? Which is 1 plus x, so 1 plus 0.357. So basically, 1.36, because we needed the 3 significant figures, okay? And then finally, the concentration of HI, it's equal to 5 minus 2 times x, so 5 minus 2 times 0.357. I got an answer of 4.29 molarity to 3 significant figures, okay? That's it for question number 9. We don't have question 10, but we have questions 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20, and that's it for this chapter. Okay, so the next question was what? The next question was question 11, over here. Hello guys, so I cut off that video and I took a short break. Now I'm continuing. I'm sorry for the background noise because I have my AC on. Let's read what the question 11 says. Kp for NH4Cl solid in equilibrium with NH3 gas plus HCl gas is 1.0 times 10 to the power of minus 2 at atm squared at a particular temperature. What are the partial pressures of NH3 and HCl at equilibrium? First of all, let's get Kp, right? Kp at equilibrium, excuse me, let me go up again. Kp at equilibrium, it's going to be the concentration of HCl times the concentration of NH3 divided by what? Divided by 1. Why? Because this is a solid, we cannot include it. It's not homogeneous, right? So I end up with this, right? So if I wrote my equation, NH4Cl solid in equilibrium with NH3 gas plus HCl gas, right? What would I end up with? Let's say this is ICE. Initially, this is 0, this is 0. This does not get anything. This does not get anything as well. So here, I add x, okay? I also add x over here. So here, I'll end up with x and x. So if I substitute the values, I get Kp, which is 1.00 times 10 to the power of minus 2. It's equal to x squared. So I'm going to need to do radical on both sides. I will get that x is equal to 0.100 atmospheres. So the partial pressure of HCl is equal to the partial pressure of NH3, which is equal to 0.100 atmospheres. That's it for question 11. We'll move on to question 12. What does it say? 2 grams, this is the mass of calcium carbonate, CaCO3. What is the molar mass of calcium carbonate? So the molar mass is 100 gram per mole. Okay, decomposes at a temperature of 1100 Kelvin in a 1 decimeter cubed. So this is the volume. Closed flask according to the following chemical reaction. What is the mass of CaCO3 solid left when the equilibrium is reached? They gave us the molar mass of CaCO3 over here. So actually, Kc, it would be equal to what? It would be equal to the concentration of products to the power of coefficient. I can't put this because it's solid, divided by the 1 because this is also solid. I can't include it. So Kc, it's equal to the equilibrium concentration of CO2. So that means the equilibrium concentration of CO2 is 1.2 times 10 to the power of minus 2. Now, I have the volume, right? What would I be able to find with the volume? I would be able to find the number of moles of carbon dioxide. Number of moles is equal to concentration times volume, so it's going to be 1.2 times 10 to the power of minus 2 times the volume, which is 1 decimeter cubed. So the number of moles of carbon dioxide, I have them to be 1.2 times 10 to the power of minus 2. Now, this is in a 1 to 1 to 1 ratio. That means the number of moles of CaCO3, it's also going to be 1.2 times 10 to the power of minus 2. Now, they want what? They want the mass of CaCO3 left. So actually, when I'm solving like this, I am calculating what? I'm calculating the number of moles of CaCO3 consumed, okay? How do I find the number of moles of CaCO3 left? It would be the number of moles of CaCO3 originally minus the number of moles of CaCO3 consumed, okay? So let's find the number of moles left of CaCO3. It would be equal to what? It would be equal to, okay, let's find the number of moles originally. We have the mass and we have the molar mass, so it's going to be mass divided by molar mass. So it's going to be 2 divided by 100, okay, minus the consumed number of moles of CaCO3, which is what? Which is 1.2 times 10 to the power of minus 2. You put it on your calculator, I got an answer of 8.0 times 10 to the power of minus 3 mole. So this is the remaining number of mole of CaCO3. Now, how do you find the mass? You should know mass over molar mass is number of moles. So the mass is equal to the number of moles, which is 8.0 times 10 to the power of minus 3, times the molar mass, which is 100, and we'll put it to the appropriate unit, which is, the appropriate significant figures, which is 2. So it's going to be 0.80 grams, and there you go. This is the mass of calcium carbonate. Okay, we'll move on now to question 13. What does it say in question number 13? What does it say? NOCl2 gases were introduced into a sealed container at initial pressures of 16 atmospheres and 12 atmospheres, respectively, and allowed to react and reach equilibrium. At equilibrium, the total pressure of the gases was 24 atmospheres. Calculate the value of Kp. So first of all, let us do the ice table. So ICE. What was the initial pressure of NO? It was 16 atmospheres. Of Cl, it was 12, and of NOCl, it was 0. Now, logically, I have 0 pressure on the right side, so my forward reaction would move to give pressure to the right side, right? So I'm losing from here and I'm gaining over here. 2, I have a 2 as my coefficient, so I'll multiply my x by 2. I have 1 as my coefficient, so I'll have a singular x. I have 2 as my coefficient, so I'll multiply my x by 2. So 16 minus 2x, 12 minus x, plus 2x. Now, this is at equilibrium, the total pressure of all of the gases. Let's find the value of x to find the pressure of each gas, okay? So that would mean 16 minus 2x, okay, plus 12 minus x. Plus 2x is equal to what? It's equal to the total pressure, which is 24 atmospheres. 2 minus 2x plus 2x disappears. 16 plus 12, that's 28. 28 minus x is equal to 24 atmospheres. So x is equal to 4 atmospheres. That means for the partial pressure of NO gas, it's going to be what? It's going to be 16 minus 2 times 4, so it's going to be 8 atmospheres. The partial pressure of Cl2 gas, it's going to be 12 minus 4, which is also 8 atmospheres. And then the partial pressure of NOCl gas, it's going to be what? It's going to be 2 times 4, which is also 8 atmospheres. So now they want to find the value of Kp. Kp, it's the concentration, or no, it's pressure now. So the partial pressure of NOCl gas to the power of 2, because the coefficient is 2, divided by the partial pressure of Cl gas, times the partial pressure of NO gas squared. So you put it and you substitute the value. So 8 squared divided by 8 times 8 squared. So 8 squared over 8 times 8 squared. So I put it on my calculator. I'll get 0.125. But I had what? I had 2 significant figures, right? Let's see the smallest value. Actually, here, this would be 8.0, 8.0, and 8.0 atmospheres. Why? Good question, because when you're subtracting, you only care about the decimal places, not about the significant figures. So when I was doing 28.0 minus x is equal to 24.0, I only care that I have one decimal place in the end, so I'll end up with 4.0. So that's why I have 8.0. Okay, so that's why I have two significant figures. So this would be 8.0, 8.0, 8.0. So my answer would be 0.13. Okay, is there a specific unit? This and this cancels, so it would be this times 1 over Pascal. Or no, 1 over atmosphere, excuse me, because it's an atmosphere. So that's it for question 13. We'll move on now to question 14. What does it say? It says, consider the following reaction. What does it say? Solid carbon and and carbon dioxide gas at 1160 Kelvin were placed in a 2-liter rigid container, and the reaction represented above occurred. As the reaction proceeded, the total pressure in the container was monitored. When equilibrium was reached, some carbon still remained in the container. So we look at the results, and we look at the time, and we look at the total pressure. We can know when equilibrium reached. How do I know? When the pressure stays the same. Okay, it does not change after some time. So here, I know my equilibrium reached. That means my equilibrium pressure is 4.18. Now this is the total pressure of gas. So total pressure at equilibrium is 4.18. They gave me for the reaction mixture at equilibrium, the partial pressure of carbon dioxide gas is 0.82. So the partial pressure of CO2 at equilibrium is 0.82 atmospheres. Now, I do believe they will ask us to find what... Oh, excuse me. I did not mean to go down like that. Actually, let's go down. They're saying... calculate in part I the partial pressure of carbon dioxide and part I the equilibrium constant Kp. So, let me just, excuse me. Let me bring it like this. Okay. So now they want to find the partial pressure of carbon monoxide. We know that the partial pressure of carbon monoxide plus the partial pressure of carbon dioxide is the total pressure. So the partial pressure of carbon monoxide is the total pressure, which is 4.18, minus the partial pressure of carbon dioxide, which is 0.82. So I care about about decimal places. So I have 2 decimal places at the end. I should end with 2 decimal places. So the partial pressure of carbon monoxide, it's going to be 3.36 atmospheres. So that's it for part I. For part II, they want us to find Kp. So Kp, it's equal to what? What's the equation? Kp, it's equal to the partial pressure of CO gas, okay, and it's squared because the coefficient is 2, divided by the partial pressure of CO2 gas to the power of 1 because it does not have any coefficient, so that means 1. So that's going to be what? That's going to be 3.38 squared divided by 0.82. I got an approximate answer of 14 because this is 2 significant figures. That means I need my answer to be to 2 significant figures. So my approximate answer is going to be 14. That's it for part AI and II. Now, part B, what does it say? If a suitable solid catalyst was placed in the reaction vessel, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure? Justify your answer. We know that a catalyst does not affect the equilibrium position. What does a catalyst do? It only allows the reaction to reach equilibrium faster. So, it does not affect the concentration of reactants. It does not affect the pressure of reactants. It does not affect anything to do with the reactants. And same with the products. It does not affect anything with that. The only thing it does is that it allows the reaction to reach equilibrium faster. So, we will reach the equilibrium faster. So then the final total pressure of the gases would stay the same because nothing is really changed, okay? Now we'll move on to question 15. So question number 15, what does it say? Answer the following questions regarding the decomposition of arsenic pentafluoride, ASF5. A 27.9 gram sample, this is the mass of ASF5, is introduced into an evacuated 10.5 liters. So this is the volume container at 105 degrees Celsius, this is the temperature. They said, what's the initial molar concentration of ASF5 in the container? Now, look what we can do. They want the concentration. We know concentration times volume is equal to number of moles, but we also know number of moles is equal to mass over molar mass. I have my mass, I can find the molar mass. I have my volume, so I can find my concentration. Concentration times volume is equal to mass over molar mass. So concentration is equal to mass over molar mass times volume, right? So what is the molar mass of ASF5? It's 169.6. I did the calculation, 169.6. So my concentration is going to be 27.9 divided by the molar mass. Sorry, because I keep on talking all day and I'm talking so fast while explaining. I mess up my words. So my molar mass is 169.9 times what? Times my volume, which is 10.5 liters. So you put it on your calculator. I got an answer of 0.0156 molarity to 3 significant figures. 1 to 3, this is 4, but this is 3. So you take it to the least amount of significant figures. That's it for part A. Now, at 105 degrees Celsius, ASF5 decomposes into ASF3 gas and F2 gas according to the following chemical equation. In terms of molar in terms of molar concentration, write the equilibrium constant expression for the decomposition of ASF5. So the K, it's going to be equal to the concentration of products to the power of their coefficient times concentration of products to the power of coefficient divided by the concentration of reactant to the power of their coefficient. So this is it. Now, pay attention. When equilibrium is established, 30% of the original number of moles of ASF5 has decomposed. That means 70% remains. They want us to calculate the molar concentration of ASF5 at equilibrium. If 30% decomposes and 70% remains, I'm going to take my original concentration, I will multiply it by 70%, which is what remained, and I will get my answer to be 0.0109 molarity. So that's it for part I. For part II, they said using molar concentrations, calculate the value of equilibrium constant. So what I could do now is I can do the ICE table, but I'm going to need some space. So ICE. Okay, now for ASF5, initially it was 0.0156 molarity. It went down to 0.0109 molarity. So it lost, right? And here the coefficient is 1, so minus x. ASF3, initially it's 0, F2 it's initially 0. So it will gain x because the coefficients for them are 1. So we can find the value of x. X is equal to 0.0156 minus 0.0109. So I got the value of x to be 4.7 times 10 to the power of minus 3. So now this is 4.7 times 10 to the power of minus 3 and 4.7 times 10 to the power of minus 3. Okay. Now what do they want? They want the value of the equilibrium constant K. So I'll just substitute. K is equal to 4.7 times 10 to the power of minus 3 times 4.7 to the power of minus 3. So I just squared it, divided by the concentration of ASF5, which is 0.0109. Put it on your calculator. Divided by 0.0109, I got an answer which is 2.03, because I used the values my calculator gave me. I got a different answer than what they got. Okay, so 2.03 times 10 to the power of minus 3. Is there a unit? Actually, yes, there is a unit, because this will turn out to be m squared over m. So I cancel this and I will be left with m. So it's this mole per decimeter cubed. Okay, that's it for part II. Now, another way they did it, I looked at the marking scheme, and what they did was, instead of finding the value of x, they multiplied this by 30%, and they said, okay, if 30% was used, that means here and here, it would be the values, right, that would take the 30%. So then it will end up being this over here. So they got the more accurate values. With these more accurate values, they were able to get the answer. The answer that they got was 2.01 times 10 to the power of minus 3. Now, part D, what does it say? Calculate the mole fraction of F2 gas in the container at equilibrium. Now, we know the mole fraction, it's going to be what? Of F2 gas. It's going to be the number of moles of F2 divided by the number of moles of F2 plus the number of moles of ASF3 plus the number of moles of ASF5. Now, we know that the number of moles, it's what? It's concentration times volume. And since they all have the same volume, I could do what? I could take out volume times concentration of F2, okay? Volume times concentration of F2 plus concentration of ASF3 plus concentration of ASF5, right? So, now what can I do? I can cancel volume and volume, and now I'm left with this equation. This would give me the mole fraction of F2 gas. If I use this or if I use the number of moles, I'd end up with the same exact answer. So what's the concentration of F2? The concentration of F2, it's 4.7 times 10 to the power of minus 3. Now, divided by what? Divided by, so it's gonna be 4.7 times 10 to the minus 3 divided by 4.7 times 10 to the minus 3 plus 4.7 times 10 to the minus 3 plus 0.0109. I got an answer of 0.231. That's it for question number 15. We now move on to question 16. Part I don't think we have it. We don't need to do it, okay? Anyways, we'll move on to question 16. What does it say? 2 HBr gas in equilibrium with H2 gas plus Br2 gas, okay? After 2 mole sample of HBr is placed in an evacuated 1 liter, so you have number of moles divided by volume, the concentration is 2 molarity. Actually, to the correct significant figure is 2.0 molarity. At 700 Kelvin, the reaction represented above occurs. The concentration of HBr as a function of time is shown below. Write the expression for the equilibrium constant Kc of the reaction. So it's going to be concentration of Br2 multiplied by concentration of H2 divided by concentration of HBr squared. Now, what's the concentration of HBr at equilibrium? So HBr starts with 2, and then at equilibrium, it's approximately what? It's approximately here. So it's 1.8. It's actually 1.80 molarity, okay? Now determine the equilibrium concentrations of H2 and Br2. So here we just need to apply the ICE table. So I, C, E. Here initially it was 2, here it was 0, here it was 0. So here we did minus 2x and we ended up with 1.8. That means x is gonna be what? X is gonna be 0.10. So here it's gonna gain x, here it's gonna gain x. So then here it's 0.10, here it's 0.10. So the equilibrium concentration of H2 and Br2 is 0.10. So for both of them, it's the same value, which is 0.10. Now, on the graph, make a sketch for how the concentration of H2 changes with time. So it starts with a 0, and then it just increases until it's 0.1. So it's something like this, right? Now, part EI, we don't have EII, so don't do it, okay? Even though it's like very logical to do it, but just like we're not gonna do it. Calculate the value of the following equilibrium constant at 700. Now that I have the concentration of H2 and Br2, and I know the concentration of HBr at the equilibrium, and I have the equation, I can substitute the value. So 0.1 times 0.1, so 0.1 squared, divided by 1.80 squared, so I got an answer of 3.1 times 10 to the power of minus 3. So now, Kp, if you want, let's do it. Let's do EII. There's no harm in doing it. Kp, use the equation Kp equals Kc whatever, where delta N is the number of gaseous products minus the number of gaseous reactants. So, the number of moles. I have 2 moles here, I have 2 moles here. So 2 minus 2 is 0. Okay, that means delta N is 0. So over here I have what? I have 0. So Kp is equal to Kc, and RT to the power of 0 is what? Is 0. So Kp is equal to Kc. That means Kp is equal to 3.1 times 10 to the power of minus 3. That's it for question 16. We move on now to question 17. The particulate diagram below represents an equilibrium mixture of N2 gas, H2 gas, and NH3 gas in a 1 liter sealed flask. Okay. Each particle is shown below. It represents 1 atmosphere of that substance. Okay. So what's the value of the equilibrium constant Kp? So what we could do is we could find the partial pressure of N2, the partial pressure of 3H2, or no, just the partial pressure of H2, and the partial pressure of NH3 just by counting whatever we have. So N2, it's this one. So let's count how many we have. We have 1, 2, 3, 4, and 5, and 6. So we have 6 N2. H2, it's this one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 H2. And then the NH3, we have 1, 2, 3, 4, so it's 4. So Kp, actually, they want us to find Kp. The equation for it, it's going to be NH3 to the power of 2 divided by N2. We're dealing with the pressure, excuse me. Oh no, Kp. Okay, anyways. So it's going to be partial pressure of NH3 to the power of 2 divided by partial pressure of N2 times partial pressure of H2 to the power of 3. So Kp, it is what? Kp, it's equal to the partial pressure of NH3 squared, so it's going to be 4 squared, divided by partial pressure of N2, which is 6 times partial pressure of H2 to the power of 3, divided by 10 to the power of 3. I got an answer of 2.7 times 10 to the power of minus 3, and that's it for question 17. We'll now move on to question 18, and then 19 and 20, and we are done. So let's do 18. What does it say? We have H2 gas plus Cl2 gas in equilibrium gives me 2HCl. 2 mole per decimeter cube. Let's just separate them into the ICE table. So ICE. 2 mole per decimeter cubed of each H2 and Cl2 is introduced into the beaker. So 2 molarity, 2 molarity. Okay, so let's just do 2.0, 2.0. Here, it's what? It's 0, right? So what happens? because we don't have any concentration in the product side, the forward reaction occurs. So this is minus x minus x. Why did I know it's minus x? Because the coefficient is 1, and it's losing. And this is plus 2x. So then, they said what? They said, give the expression of concentration of Cl2 at equilibrium in terms of Kc. So, what is Kc? Excuse me. Let me just move this. Kc, we know it's equal to the concentration of HCl squared divided by the concentration of Cl2 times the concentration of H2. So it's gonna be Kc, it's equal to 2x squared divided, so 2x all of it squared, divided by 2 minus x times 2 minus x, so also squared. Okay, so if I do radical on both sides, what do I get? I get Kc is equal to, radical Kc is equal to 2x over 2 minus x. So I can move this to the other side. What do I end up with? So 2 radical Kc minus x radical Kc. Okay, it's equal to what? It's equal to 2x. Okay. So now let's try at first to find only the value of x. So I could move this to the other side. So I'll get 2 radical Kc is equal to 2x plus x radical Kc. I take x as a common factor. So 2 radical Kc is equal to x times 2 plus radical Kc. Then I divide both sides. So x is equal to 2 radical Kc divided by 2 plus radical Kc, right? Now, they want what? They want the expression of concentration. So x is not the concentration of Cl2. The concentration of Cl2 is 2 minus x. So it's going to be 2 minus 2 radical Kc over 2 plus radical Kc. So to actually solve it, we need to give them the same denominator. So we'll multiply this by 2 plus radical Kc up and down. So I will get 4. 2 times 2 is 4 plus 2 radical Kc, right? Divided by 2 plus radical Kc. So this and this cancel. And now I'm left with what? I'm left with 4 over 2 plus radical Kc. So this is the expression with K. Okay, that's it for question 18. There's still 19 and 20. Move on to question 19. What does it say? Hydrogen gas is produced by reacting carbon monoxide with steam. Okay, at equilibrium, the concentrations of the species present in the reaction mixture are the following. If initially equal concentrations of reactants and products were mixed in a closed vessel, deduce the direction favored by the equilibrium position. So they said initially we had the same amount of reactants and products, right? So we had X and X. Then all of a sudden, let's do the ice table, you know? It's easier to explain it with the ice table. ICE. Excuse me, it's entering here. Let me just erase this. So ICE. Initially, I had X, 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 X for all species, same amount of products and reactants. Then something happened. I ended up with 0.53, 0.53, 1.47, and 1.47 as well. So logically speaking, looking at it, that means I lost an amount here, I lost an amount here. But I gained an amount here and I gained an amount here, right? So in which direction did it travel? If my reactant's concentration increased, that means it traveled backwards. So the equilibrium position favors the backward reaction. And anyways, what you could do is you could find the, what's it called? K equilibrium. K equilibrium, it would be equal to what? It would be equal to 0.5, like the concentration of products to the power of their coefficient, so that's 0.53 squared divided by 1.47 squared, so I got 0.129. Then I find the value of Q. Q, it's gonna be x squared divided by x squared, which is 1. So Q is greater than K equilibrium. Because of this, I can say that the backward reaction is favored. That's it for question 19. And now finally, last but not least, the last and final question, fill in the table to predict the effect. Now, one thing you should know is that the equilibrium concentration, or like K, equilibrium, sorry, not concentration, the equilibrium constant, it's only affected by temperature. This temperature is the only thing that will affect it. So let's read. I have this over here and I have my delta H to be negative. If my delta H is negative, that means my temperature is on the product side. Now what happens if I increase my temperature? Then there is a change. There is an unstable balance. I have excess temperature, so I need to shoot it to the other side with less temperature, which is the left side. So equilibrium position shifts to the left. Now remember, temperature is the only thing that affects the equilibrium constant. So if I shift it to my left, the concentration of my reactants increases. Since my concentration of reactants increases, then what will happen to a K equilibrium? It will decrease, okay? Now, increasing the concentration of SO2. If I increase the concentration of SO2, I'll have an excess SO2. I need to get rid of it to maintain equilibrium, so I will shoot it to the other side. So equilibrium shifts to the right? And here, there is no effect because it's not temperature. Okay, so for all of them, it's no effect because they're all not temperature. Now, increasing the pressure. Here I have how many moles of gas? Here I have 3 moles of gas. Here I have only 2 moles of gas. So if I increase the pressure, it will shift to the side with the less moles of gas, which is what? Which is the 2SO3. So it will shift to the right. Adding a catalyst has no effect on the equilibrium position. It just helps reach equilibrium faster, okay? That's for part A. Now for part B, that the H is greater than 0. That means my temperature is on the reactant side. If I increased my temperature, I have an excess in temperature. I need to get rid of it. So my equilibrium position shifts to the right. So the concentration of my products increases. So my K equilibrium increases. Now, temperature is the only thing that affects. So everything else will be not affected. If I increase the concentration of H2, I have excess H2. I need to get rid of it, so I shoot it to the other side, so it will shift to the left. Okay, if I increase the pressure, I have 2 moles of gas here and 2 moles of gas here. If I have the same number of moles, the increase and decrease of pressure will have no effect. And then finally, adding a catalyst has no effect. So thank you guys for watching. That's it for the chapter 3 CQDs. I hope you enjoyed, and see you in the next chapter, which is chapter 4. Hello guys, welcome to the next part of the video. We're gonna move on to chapter 4. So chapter 4, we have the 2 main sections, which are 4.2 and 4.3. We have only questions 7, 13, and 15 until 20. So let's get started with question number 7. Explain how to compare the strength of different acids based on structure. So, before we get started with these 2 comparisons, let me discuss the strength of acids in general. We have many different types of comparisons, but there's 3 main ones we need to focus on. Of course, all organic acids, that mean any acids that's like CH3, COO, whatever, COOH, these are weak acids, okay? But when it comes to comparing, for example, halogen halides, for example, HF, HCl, and HBr, this is the example they are talking about. Why is HF? They're saying that HF is weaker than HCl, and then HCl is weaker than HBr. Why exactly is this? Of course, I'm going to add the last and final one, which is HI. Very simply, you need to think about the bond length and bond strength. When it comes to bond length, you need to also relate it to the bond strength, okay? So let's first think about the bond length. As we go down the group from fluorine to iodine, the number of electrons increases, so the number of shells increases, so the atomic radius, the distance from the nucleus to the outer electrons, increases. The more this increases, the weaker the force of attraction from the nucleus to the outer electrons becomes, okay? The easier it is to take away the electrons, right? This is something very important. Now, the easier it is to take away the electrons, the weaker it's gonna be the bond strength. So this has the weakest bond strength. So BS means bond strength. Actually, let me just write weakest strength. Okay? So HI has the weakest bond strength. Why? Because the outer electrons are the farthest most from the nucleus, whereas HF has the strongest bond strength. Now, what is the definition of an acid? The definition of an acid, according to Bronsted-Lowry, it is a proton donator. And when we're talking about the proton, the main thing we should think about is what is hydrogen. So, if it releases hydrogen, the more hydrogen it releases, the stronger an acid, because an acid is a proton donor. So, the more hydrogen it releases, the stronger an acid it is. This has the weakest bond strength. Why? Because it has the longest bond length. But because of this, it can release hydrogen more easily than HF. So thus here, this is the weakest acid. And this is the strongest acid out of all of these. So basically, you memorize this trend like this. If they asked you why, you would say that the bond strength of hydrogen fluoride is greater than the bond strength of hydrogen iodine. And like, for example, HF has a greater bond strength than HCl, HCl greater than HBr, HBr greater than HI. Thus, it is harder to it requires more energy to break the XH bond, okay? And it's harder to release hydrogen, so the weaker the acid, right? So that is the first of the comparisons. Now the next of comparisons, it's anything, any acid. For example, here the examples they gave us, HClO4, HClO3, and HClO2. How can we compare these? First of all, they all share HCl as something common. The only thing that differs is the number of oxygens. Now, the main rule you should know is that the greater the number of oxygens, the stronger the acid. But why? Very simply, the more oxygens we have, oxygen, it is what? It is a very electronegative atom. So it's gonna have a great electron pulling force. So the more oxygens you have, you will have a greater electron pulling force, okay? So what does this cause? The oxygens will then cause the electron density around the hydrogen to become less, right? So there's less electrons around the hydrogen because the oxygens are pulling them all because they're more electronegative. So what happens to the hydrogen? It's easier for us to break it. So basically, the more, the greater number of oxygens I have in my acid, the stronger it is. Why? Because of the electronegativity and because the oxygen will cause the electron density around the hydrogen to lower, so then it will be easier to break the bond and then we will release more hydrogen. So this is stronger than this, stronger than this. And now what if they gave us an example? For example, they gave us HOF, HOCl, HOBr, HOI. Which one of them would be stronger? Here, you don't think in terms of if I go down the group, the bond strength and bond length. No. When you have oxygen, okay, and it's playing a part, right? You think in terms of electronegativity. So oxygen is an electronegative atom. So the greater the electronegativity, right, the more it will affect the electron density around the hydrogen, the easier it will be to break the bond. So that means that HOF is a stronger acid than HOCl, which is stronger than HOBr and stronger than HOI. Why? Because it contains the more electronegative atom, okay? Very simply, this is how you solve and explain for all the different types of acids based on their structure. So that's it for question number 7. I'll now move on to question 13. What does it say in question 13? It says identify the conjugate acid-base pairs in the following reaction. So, first of all, we need to know the definition of an acid and a base. According to Bronsted-Lowry, the acid is a proton donor, whereas the base is a proton acceptor, right? So, very simply, NH3 gas, it turns into NH4 plus aqueous. So what happened to the NH3? It accepted a proton, so that makes NH3 a base. H2O liquid turned into OH minus. What happened to H2O? It donated a proton, so it's a proton donor, so it's an acid, right? Now, here's the interesting part. The base, once it gains the proton, it turns into a conjugate acid. And the acid, once it loses its proton, it turns into the conjugate base. Now, what do we mean by this? When the base gains the electron, it now has the ability to give an electron. So now it's a conjugate acid. When the acid loses its electron, or the proton, sorry, excuse me, not electron. When the hydrogen donates, when H2O donates its proton, right, it now has the ability to gain a proton, so thus it turns into a conjugate base, okay? This is very simply the definitions. Now, let's see again. HC3H5O3 gas turns into C3H5O3 minus. So what did it do? It donated the proton, right? So it is an acid. Then H2O, what did it do? It gained the proton, so it is a base. And the acid will turn into a conjugate base after it loses the proton, and the base turns into the conjugate acid after it gains the proton. And last but not least, we have CH3NH3 plus turns into CH3NH2. What happened? It donated a proton, so this is the acid. H2O turned into H3O plus, so it accepted the proton, so it is a base. That makes this the conjugate base, and this is the conjugate acid. Okay, that's pretty much it for question number 13. Next up, we have questions 15 until 20. Let's get started with question 15. What does it say? It says consider the indicator below HIN, which is a weak acid. The equilibrium of HIN in water and the colors of the different species in the solution are given below. How would the color of the indicator change if added to an aqueous solution of an acid or base? So you need to think of it like this. If I added an acid, what does an acid do? Let's say this is like my box. I have this reaction occurring and I added an acid. What does an acid do? My acid is a proton donor, so it would increase the concentration of H+. Now, according to Le Chatelier's principle, I have an unbalance in my equation, so I need to balance it. If I have an increase, I will need to shift it to the other side, right? So I will shift it to the other side. So what happens now? The concentration of HIN, what happens to it? It will increase, whereas the concentration of IN minus would decrease. So what would the color of my indicator turn to? My indicator color would turn red, okay? So I hope you understood that. When you're adding an acid, what does the acid do? It releases the proton. What does the proton do? It increases the concentration of H+. According to Le Chatelier's principle, we need to balance it out by sending it to the other side. So the concentration of HIN increases, concentration of IN minus decreases. So my solution will turn red. Now, let's do the same exact thing, but we have a base. So now we have a base. What does the base do? It is a proton acceptor. So it will take the H+. So the concentration of H+ would decrease, right? So what happens? According to Le Chatelier's principle, we have a change. The change is a decrease. We cannot have a decrease. To counteract the decrease, we need to take from the other side. So now my equilibrium will shift to the right. So what happens? My concentration of HIN decreases, whereas the concentration of IN minus increases. So what happens to the color of my indicator? It will turn yellow. Okay, that's pretty much it for question number 15. We'll move on to question 16. What does it say? Okay. Given the two equations, NH3 plus H2O in equilibrium gives me... okay, before I continue with this, okay, let us identify the conjugate, the acid, the base, the conjugate acid, and the conjugate base. NH3 plus H2O in equilibrium gives me NH2 minus plus H3O plus. NH3 turned into NH2 minus, so it gave away a proton, so it's a proton donor, so it's an acid. H2O turned into H3O plus, so it accepted the proton, so it is a base. The acid turns into a conjugate base, the base turns into a conjugate acid, okay? Now, for NH4 plus H2O, NH4 plus turned into NH3, so it donated the proton, so it's an acid. H2O turned into H3O plus, so it gained the proton, so it's a base. So the acid turns into a conjugate base, and the base turns into a conjugate acid. They said identify the conjugate acid-base pair in each reaction. We figured it out already. Now, in part B, they said specify the Bronsted acid and base in each of the equations. We also figured it out as well. Now in part C, what are they saying? They're saying draw the particulate diagram showing the composition of the mixture at equilibrium for equation 1, assuming that the percent dissociation of ammonia in is 25%. Note that the water particles are not depicted in the diagram. So they're talking about equation 1, right? What's happening in equation 1? We have NH3 plus H2O. What happens to my NH3? It will turn in equilibrium, of course. Don't forget that you're dealing with equilibrium. It will turn into NH2 minus and H3O plus. Now, excuse me for a bit. I need to go down and see what they were discussing about. And let me rewrite the equation. Equation 1. It was what? It was NH3 plus H2O in equilibrium will turn into NH2 minus in addition to H3O plus, okay? They said it's 25% dissociation, right? So let's count the number of moles I have of NH3. They don't count water initially, so we're gonna ignore it. So let's count the number of moles initially of NH3. I have 1, 2, 3, 4, 5, 6, 7, and 8 moles initially. So my 8 moles of NH3 initially, what happened to them? 25% of it only came to the other side, like 25% of it reacted. So what does this mean? If I had 8 moles, and we're not caring about the water because in this case the NH3 is the limiting reagent, okay? And only 25% of it reacted. What's 25% of 8? It's 2. That means I'll end up with 2 moles of NH2 and 2 moles of H3O plus. So if I was to draw it, how would I draw it? Before I continue, I should know what happened. Some of my NH3 decomposed, right? How much decomposed? 2 moles decomposed, right? So I will need to get rid of 2 particles. So I get rid of this. If you want to think about it in a certain way, you could take it like this. You have this, and you have this, right? And let's say that this is a water molecule because they didn't draw the water molecules. So what's gonna happen is, oh, here it's minus, by the way, excuse me, is basically the NH3, it dissociated. So we took away one of the hydrogens and we put it over here. We gave it to the water. And then we also took one of the hydrogens and we gave it to the water. So we'd be left with what? We'd be left with NH2 minus and H3O plus. So I have now how many? 1, 2, 3, 4, 5, 6 NH3. So let's draw 6 NH3. So 1, 2, 3, 4, 5, and 6 NH3. And don't forget to include your 2 NH2, right? And your 2, what? Your 2, let me get the green color. Your 2 H3O plus. Okay, this is something very, very, very important. So very simply, this is what your answer is supposed to look like, okay? That's it for question part C. We'll move on to part D. It says a student claims based on the given equations 1 and 2, NH3 can act as an amphoteric. Do you agree? NH3, here we said it was what? It was an acid. And here we said it was a conjugate base. So what does this mean? Very simply, it's acting as an acid in the first equation. In the second equation, it's acting as the conjugate base of an H4+. So it can be amphoteric because it has the properties of both an acid and a base. Okay, so yes, I do agree with the student. So now the next question is question 17, 18, 19, and 20. Let's get started with question 17. Let's see what it says. A 25 milliliter, this is the volume, sample of hydrochloric acid solution is titrated using this much. This is the concentration, NaOH solution, and phenolphthalein as an acid base indicator. The endpoint is reached upon the addition of 13 milliliters. So this is the volume for the NaOH, of NaOH, right? The neutralization reaction that occurs. So we have hydrochloric acid, right? We add to it an AOH. When an acid and a base react, they undergo neutralization, but now we're dealing with a strong acid and a strong base. So they will fully dissociate, or not fully dissociate, they will fully react to give us what? To give us water and a salt. Okay, what's the salt gonna be? Very simply, just split up your ions. I always prefer that you split up your ions. So H plus and Cl minus, Na plus and OH minus. So my salt will be NaCl and water is H2O. So I'll have H2O plus NaCl. Now they're saying name the titrant and name the analyte. When they ask you for the titrant is usually the solution that we know its concentration. Looking back, they only give us the concentration of NaOH. That means NaOH is what? NaOH is our titrant. The analyte is the solution of unknown concentration. So the analyte in this case is the HCl because they did not give us the concentration of HCl. Now they want us to calculate the concentration of the HCl solution. Now this takes us back to our equation over here. Please remember to always balance your equations. My equation is balanced and I see that I reacted it in a 1-to-1 ratio. So this is something very good and very, very important. So let me just erase these. They want to find the concentration of HCl. So if it's reacting in a 1-to-1 ratio, that means the number of moles that I used for NaOH, it's equal to the number of moles that are in the HCl. If I found the number of moles of HCl, I'd be able to find the concentration because I am given the volume. So let's start by finding the number of moles of NaOH. The number of moles of NaOH is very easy. It's the concentration times the volume. Our concentration is 0.100 mole per decimeter cubed, right? But our volume is 13 milliliters. We cannot deal with milliliters or centimeter cubed. It's either decimeter cubed or liters. So times 13 over 1000 liters. So my number of moles, it's going to be 1.3 times 10 to the power of minus 3 mole. Okay. Now this is the number of moles of NaOH. It's gonna be the same exact number of moles of HCl. Why? Because it's a 1-to-1 ratio and it goes to completion because it neutralizes, right? So the number of moles of HCl in this scenario, it's 1.3 times 10 to the power of minus 3 mole. So what would the concentration of HCl be equal to? The concentration of HCl is equal to the number of moles of HCl, which is 1.3 times 10 to the power of minus 3, divided by the volume, which is 25 times 10 to the power of minus 3, because it's in milliliters. millimeters, so I need to divide by 1,000. Put it on your calculator, and I got an answer of 5.20 times 10 to the power of minus 2 mole per decimeter cubed, and this is the concentration of the HCl solution. Okay, that's it for question 17. I'll now move on to question 18. What does it say? The concentration of H plus in a 10,000 decimeter cubed, so this is the volume sample of a monoprotic acid. Monoprotic acid means that we have one hydrogen. Okay, so we're gonna keep it as H plus because we have a singular hydrogen. Okay, they gave us what? They gave us the volume and they gave us the concentration. Potassium hydroxide, KOH, is used to neutralize the acid. So they added to it KOH and they neutralized the acid. What mass of potassium hydroxide is needed to neutralize the acid? Now, how do I know what my acid is gonna be? First of all, I don't know what my acid is, but I know it's monoprotic, meaning it has one singular hydrogen. I need to form water, so I'm gonna call this X. So let's say my acid is HX, okay, for example, because I don't know what the other part is. So I can split it up into its ions. I would get H plus and X minus. Here I split it up, I get K plus, OH minus. So here, my salt, it's gonna be what? It's gonna be KX, and my water is gonna be what? It's gonna be H2O. So it reacts fully, it forms fully. It basically works in a 1-to-1 ratio. So here I have Kx plus H2O. So they react in a 1-to-1 ratio. Because of this, I can say that the number of moles used in HX, it's equal to the number of moles used in KOH. So let me find the number of moles used in HX. It's very simply the concentration times the volume. So it's 1.12 times 10 to the power of minus 3, which is the concentration, times my volume, which is 10,000. Put it on the calculator, you should get an answer of 11.2 mole. Now, this number of mole, okay, I want to find the mass. I know that the number of mole is equal to mass over molar mass. So the mass of KOH used is equal to the number of moles, which is 11.2, times the molar mass, which is 56.1 gram per mole. And the answer, they used the wrong one. They used 56, but they gave it to us as 56.1, so use 56.1. So I got an answer of 628 to 3 significant figures grams. Okay, that's it for question 18. Now we'll move on to question 19. Complete the table below using strong acid, strong base, weak acid, weak base, weak acid, strong base, or strong acid, weak base. Here, this does not have anything to do with, oh, I need to do any calculations. No, this is about common sense. This is about logic. I need to know, first of all, what is the strong acid, strong base? That means I'm going to have a low pH over here, and I will have a very high pH over here. Weak acid, weak base, I will have moderate for both of them. Weak acid, strong base, I will have a moderate, right, pH over here. Whereas here I will have a very high pH. Or strong acid, weak base, here I will have a low pH. Here I will have a moderate pH. So here this is something very important. You need to pay attention to it. It's really critical. So the first type that I am dealing with, let's see. I'm starting over here. I can see that I have a pH of 13. That means I'm starting off with what? I'm starting off with a strong base because it has a very high pH. But then I'm coming over here. I'm seeing my pH is 4. And as you can see here, it's more flat. It's relatively flat and then it falls. But here it's what? It's increasing and then it curves. So because it's increasing and curves and it starts at a relatively high pH compared to regular acids, then I can say that I'm dealing with a weak acid and a strong base, which is the case. Okay, we'll move on to the next example. Here, as you can see, it's relatively flat, then it increases, and the pH is 1, which is really low. But here, as you can see, it's curving, and then it goes down, and it's starting from a pH of 11, which is moderate. It's not that high. So it seems that I'm dealing with a weak base and a strong acid. But please pay attention, always put the acid first. I'm just saying it like this because I want to get over with it, you know? So it's a weak base, strong acid. You should say it's a weak acid, strong base. Or here, for example, here you should say it's a strong acid, weak base, okay? Now here, as you can see, this is strong. And this is also strong. This has a pH of 1, this has a pH of 13. So I'm dealing with a strong acid and a strong base. Okay, now, last but not least, the last diagram. Here it's curving and it goes up. This is also curving and it goes down. Here this has a pH of 5. Here this has a pH of almost 10. So I'm dealing with a weak acid and a weak base. Okay, that's it for question 19 part A. Now we'll move on to question part B. They said, given the following indicators with pH range of color range, they want us to say, when do I use this indicator? Do I use it strong acid, strong base, strong acid, weak base, weak acid, strong base, and weak acid, weak base? So go back to what I'm looking at here. There's something very important you need to pay attention to, which is the midpoint. So you need to try to find the midpoint, so halfway between these. For example, here, halfway is approximately 9. So I need to find a pH that has my range that will have a value of 9 somewhere. Here I come again. Where's halfway? Halfway, for example, here it's for me 4. So I need to find a pH that has 4 in the range, and that's almost halfway. Here, where's midway? Midway is exactly 7, so I need a pH that has my values and that has 7 in the midst. And here as well, my midpoint is also 7, so I also need an indicator that's 7, maybe slightly like stronger, slightly weaker, you know what I mean, depending on what I'm dealing with. So, actually, let's get started. There's a trick I forgot to mention. Now I will be able to mention it. A strong acid and a strong base. We said that their midpoint was at 7. So I need something that has a range of 7. So I look at my answers. This is the only option that has a range of 7. So for my first part A, I will choose bromothymol blue. Now I have a strong acid and a weak base. Strong acid and weak base, my pH is gonna be more acidic. So I need to choose something that has its values more acidic, but not too acidic. This is very important. We're not dealing strong acid, weak acid. We can't deal with that. No, this you choose something really super duper acidic. No, here we're dealing with a strong acid and a weak base. So we choose something more to the acidic side, but it's still close to 7. So this would be my answer over here. Methyl red is my answer. Now, a weak acid and a strong base. Again, I need something that's higher than 7. Why? Because I have a strong base, but it should not be too high. It should be close to 7, near 7. So if I choose between this and this is going to be the winner. Why? Because it's closer to 7. So this is the correct answer. Now, for part IV, I'm dealing with a weak acid and a weak base. Because both of them are weak, there's no suitable indicator. Okay? So that's it for question 19. We'll now move on to question 20. What does it say in question 20? Question 20 ranges a lot, actually. It's until part F. So let's see what it says. A solution of 0.100 molarity, this is the concentration, HCl, and 0.100 molarity, this is the concentration again, NaOH, are prepared. A 40 milliliter, so this is the volume sample of one of the solutions, is added to a beaker and then titrated with the other solution. A pH electrode is used to obtain the data that are plotted in the titration curve shown below. They said identify the solution that was initially added to the beaker. So they're saying, did I initially in my beaker have the acid HCl or the base NaOH? Very simply, you need to look at your graph. You will look at the starting pH. The starting pH was very, 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 very low. It's 1 almost. So I will know that it's an acid. So what's my acid? My acid is HCl. So how would you answer this? You would say that the solution in the beaker was HCl, as indicated by the ascending pH versus the volume of titrant graph. So they're saying, I started with a very, very low pH, and then it got high after I added the, after I did my titration, or like after I added everything. So that means my titer, the one with, actually no, we can't say that. So we can say that the HCl was the solution that was initially in the beaker, and then I titrated it with what? With NaOH. Okay. Now part B, it says on the titration curve above, circle the point that corresponds to your equivalence point. So the equivalence point, it's gonna be this point over here, which is what? Which is on the x-axis 40.0 milliliters, and on the y-axis 7 pH. This is my midpoint. Why did I choose this? Because I'm dealing with a strong acid, which is HCl, and a strong base, which is NaOH. So of course I'm gonna have my midpoint to be the neutralization, which is 7. Now, at the equivalence point, how many moles of titrant have been added? So at the equivalence point, which is this point over here, okay, they want to know the number of moles of titrant. The titrant is the thing that I added to the beaker, which is NaOH. So they want to find the number of moles of NaOH. I have the concentration, which is 0.100. I know my volume, which is 40 divided by 1,000, because it's in milliliters, I need to change it to liters. So I will get 0.00400 mole of NaOH. Okay, that's it for part C. For part D, what does it say? It says the same titration is to be performed again, but this time using an indicator. They're saying use the information in the table below to select the best indicator. So we know that our indicator needs to have something that is in range with my midpoint. My midpoint was approximately 7. So I need to look at the values. I have 0, 1.8. This is extremely what? Acidic, so I am absolutely not going to take it. 9.5, 10.5, this is basic, so I'm also not going to take it. So the only thing I'm left with is 5.2 until 6.9. And I will choose 6.9 because it's the closest to 7. It's not exactly 7, the equivalence point, but based on what we see, we say 7. It's not exactly 7, it could be 6.9. So this is the perfect answer, which is the bromocresol purple. So that's pretty much it from part D. We'll move on now to part E. What is the difference between the equivalence point of a titration and the endpoint? This is a very important question. Good thing they asked it. The equivalence point of a titration occurs when the number of moles of titrant is equal to the number of moles of analyte. So, according to their stoichiometric ratio. So the number of moles of titrant equals to the number of moles of the analyte. Okay, this is according to stoichiometric ratio. So if the number of moles of my titrant are equal to the number of moles of my analyte according to their stoichiometric ratio, then I will say that I have reached my equivalence point. So my equivalence point is when the number of moles are equal. For example, the titrant in this case was NaOH. The analyte in this case was HCl, for example. What do they mean according to stoichiometric ratio? If I was dealing with H2SO4 and NaOH, then I have 2 hydrogens with 1 OH minus. It's not going to work out. So then you'd need to apply stoichiometry in order to get the equivalence point. But to deal with HCl and NaOH, they are already balanced according to their stoichiometric ratios. So the number of titrants and the number of moles of the titrant and the number of moles of the analyte are equal. So this is the equivalence point. And now the end point of a titration. This is when the reaction is complete and when the indicator undergoes its color change. So here we can say indicator undergoes color change. Okay? So the reaction is complete. Okay, that's it for part E. Now we'll move on to part F, which is the last part of question 20, and then we're done with chapter 4. On the grid provided below, sketch the titration curve that will result if the solution in the beaker were reversed. So they're saying, in the beaker, I have my NaOH, and then I titrated it with HCl. So instead of starting from a very low pH, I'd start with a very high pH, for example, here, and then I'd fall down. Almost. I wouldn't fall down because it's NaOH, it's strong. I'd go down here almost, and then I'd fall here, and then I'd go how? I'd go all the way, I'd come here, and then I'd fall, and I'd go all the way like this until I have a very low pH. So what did I do basically? I flipped the initial graph. So look at the initial graph. I basically flip it because I'm starting with what? I'm starting with the NaOH instead of the HCl, okay? So that's it for part F, and that's it for chapter 4. Thank you guys for watching, and then I'll see you now in chapter 5. Hello guys, how are you? So now this is the last chapter, which is chapter 5, which is about the oxidation and reduction reactions. We only have 4 questions, which are questions 3, 6, 8, and 12. So let's do them quickly, and then that would be it for part A, full entire chemistry revision. So let's get started with the very first question, which is question 3. It said, write the 2 half equations for the following redox reaction. Specify which one is the oxidation half and which one is the reduction half. So you need to take a close look at what you're dealing with. First of all, you need to deduce the oxidation number for all of them. I'm not going to explain how to get the oxidation numbers. You should know by now. Here, hydrogen is +1, Cl is -1, Fe is 0. Here, Fe is what? Fe is +2. No, Fe... Actually, yeah, Fe is +2. Cl, it's it's gonna be -2 in total, but it's gonna be divided by 2. So Cl stays -1, and then H2 is 0. So now we need to pay attention to the oxidation numbers that actually changed. So Cl, it stayed what? It stayed -1. That means we don't really care about it. Instead, we care about the hydrogen going to 0 and the Fe going to +2. So the hydrogen, it was initially hydrogen and it's H+, but how many H+ do we have? We have 2. So 2H+, it turned into what? It turned into H2. How could 2H+ turn into H2? There needs to be the addition of an electron somewhere. So what happens if my 2 positive protons, my 2H+, gain 2 E minuses? They would give me H2, which is neutral. Now the opposite, vice versa. I had Fe, a singular Fe, it turned into what? It turned into Fe2 plus, right? So how does my Fe turn into an Fe2 plus? I needed to have lost my electrons somehow, because Fe neutral turns into positive. That means it lost electrons. How does it lose electrons? Very simply, I'll put it on the other side. How many electrons did it lose? It goes from 0 to +2, so that means it lost 2 electrons. Okay. So now here you have to pay attention. They're saying which one is the redox reaction and which one is the which one is the reduction reaction and which one is the oxidation reaction. You should remember this. Oil rig. Oil rig, we're talking about what? We're talking about electrons in this case. So oxidation is the loss of electrons. Which one lost electrons? This one lost 2 electrons. So this is the oxidation half reaction. Okay. Reduction is gain of electrons. Which one gained electrons? This one gained electrons. So this is the reduction half reaction. Okay, so that's it for question 3 grid. We'll now move on to question 6 grid. What does it say? It says, okay, question number 6. Assign oxidation numbers for each element in the following chemicals. Here I need to focus because I'm gonna be explaining a general summary. So I'm not gonna explain the things that you know already. For example, like the sum of a neutral compound, it's gonna be 0. The sum of oxidation numbers is 0. I'm gonna go straight forward in what you should pay attention to. The first and most important thing, the thing that never ever changes in chemistry, is the oxidation of fluorine, which is -1. After the oxidation of fluorine comes the group 1. Group 1 metals such as sodium and Na. They always have an oxidation number of +1. Always it's +1 in compounds. After group 1, you guessed it, comes group 2. For example, Mg, it always has +2 in its compounds. Now, here comes the first exception, which is hydrogen. Hydrogen, most of the time it's +1, but we have a few exceptions. The first exception could be, actually, in the metal hydrides. For example, a metal hydride is NaH. Na, we said it's always +1, so hydrogen is going to be -1. In this example, and only in this example, do we have an exception with hydrogen, which is the metal hydrides. Okay, that's pretty much it. Okay, after hydrogen comes another exception, which is oxygen. Oxygen, most of the time, it is what? It is -2, except it has what? It has 3 very important exceptions. The first exception is H2O2, which is hydrogen peroxide. Hydrogen is heavier, not heavier, it's like more important than water in terms of oxidation number, so it would take the +1. So this would be 2 times +1 plus 2 times X, it's equal to the sum, which is 0, the sum of the oxidation numbers. So I get 2 plus 2 is equal to 0. So then 2 plus 2x is equal to 0, so then I get x to be -1. This is the first exception for oxygen. The second exception is KO2. K, we know it's a group 1, so it's going to have +1. So +1 plus 2 times x is equal to 0, because this is the sum of the total oxidation number. So I will get x to be what? To be -half. And yes, it is possible to have half or like even fractions as your oxidation number. Now, the last and final example is OF2. Okay, here, oxygen, it does not take it's not the more important one. The more important one is fluorine. So oxygen would be x. X plus 2 times -1 is equal to 0. So I got x to be what? I got x to be +2. So these are very, 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 very important examples for oxygen. These are the exceptions. Now, what comes after oxygen is chlorine, bromine, and iodine. They are less important than oxygen, so these come after oxygen. So if I'm dealing with, for example, usually most of the time they have what? They have an oxidation number of -1. But if they came in a compound after oxygen and hydrogen, of course I give the priority to oxygen and hydrogen. These I care about them least. And then everything else, for example, sulfur, nitrogen, manganese, chromium, whatever you want, these all come after. So basically this list, imagine it as a VIP list. If I come and I see in an element fluorine, I give it the very, very, very utmost respect and the greatest importance. If I see group 1, group 2, so on and so forth, you know, this is the thing that you must follow in order to be able to solve question 6. So let's start with H2O2. H2O2, hydrogen is more important than oxygen, so it takes the importance. So that's going to be 2 times plus 1 plus 2 times X is equal to 0, which is the sum of the compound. So then I got hydrogen to be what? I get hydrogen to be plus 1, and then I solve, I get X to be minus 1. That means the oxidation number of hydrogen is plus 1 and oxygen is minus 1. OF2, fluorine is more important than oxygen. So X plus 2 times minus 1 is equal to 0. X is equal to plus 2. So oxygen is plus 2, fluorine is minus 1. Na2O2, Na2O2. Na, group 1, metal is more important than oxygen, so it will take the priority. So this would be 2 times plus 1 plus 2 times X is equal to 0. So I got X to be what? I got X to be minus 1. So I have plus 1 minus 1. HOCl. HOCl. Okay. Here I'm dealing with what? I'm dealing with a halogen. Excuse me, let me fix this. No, it's pissing me off. It needs to stay still like this. Okay. So hydrogen and oxygen take the importance. So that's plus 1 minus 2 plus X. All in all, it will give me an answer of what? It will give me an answer of 0. So plus 1 minus 2, that's going to be minus 1. So minus 1 plus X is equal to 0. X is then equal to 1. So I have hydrogen to be what? I have hydrogen to be plus 1, oxygen to be minus 2, and chlorine to be plus 1. Now CO3 2 minus. This is something very important. CO3 2 minus. Okay. Carbon, I don't know what it is, it's X, because oxygen takes the greater priority. Plus 3 times minus 2, it's gonna be equal to the charge of the ion, because it's a complex ion. Or like, yeah, a compound ion, which is here, in this case, the charge is minus 2. So I'll move this to the other side. X is equal to 6 minus 2, so X is gonna be equal to plus 4. So here I have plus 4, here I will have minus 2. Now here we have Cr2, excuse me. Cr2SO4 3, so we split them into their ions, Cr3 plus and SO4 2 minus. So Cr, of course, is gonna get the 3 plus, so this is 3 plus, and then SO4 2 minus, right? This is very important. I want to find the oxidation number of X, of sulfur, so I will call it X. Oxygen is more important than sulfur, so it gets the priority. So plus 4 times minus 2 is equal to minus 2. I'll move this to the other side. X is equal to 8 minus 2, which is plus 6. So I get plus 6 here, minus 2 over here. Now here, last but not least, this is the most important one. Please pay attention. This is the CuNH3 2 plus. Now, something very, very, very important you need to pay attention to when you come across something like this. You need to have something called a ligand. What's the ligand? The ligand is something that will take the 0 as a charge, and it will give the charge to the metal. So I have a metal and something else. This, I will call it my ligand. My ligand will have a total charge of 0, so it will turn out to be NH3 2, but all in all, it has a total charge of 0. And then the 2 plus will go where? Will go to the Cu. So I will end up with Cu having a charge of 2 plus, and then I have NH3 2, which is 0, right? The 2 doesn't really affect anything. It just like does not exist, you know? So then here, I'm going to have what? I'm going to have plus 3. Or no, sorry, excuse me. Oh, I moved it. That's not nice. Let's try to fix it. Okay. So for the N, I have hydrogen, which is more important. So it's going to be X plus 3 times 1 is equal to 0. So X is going to be minus 3. So I will get plus 2, minus 3, and plus 1. And that's it for question number 6. Let's move on to question number 8. What does it say? It said using oxidation numbers, identify oxidizing and reducing agents. So they want us to find the oxidation numbers for all of the following. That's very easy to do here because this is ionic. You can split them into their ions. You get Fe3 plus and O2 minus. So this has an oxidation number of 3 plus. This has an oxidation number of minus 2. Okay, here this is minus 2. This gets an oxidation number of plus 2. Then iron Fe goes to 0. And here this is 2 times minus 2, but the oxygen is minus 2. So 2 times minus 2 is minus 4, and this turns into plus 4. I'm doing it very briefly and in my mind because you should know how to do it by now. I'm not going to sit and explain how to do every single process, okay? So anyways, the plus 3 went to 0. That means it gained electrons. If it gains electrons, that means it's reduced. So Fe2O3 is reduced to Fe. So this is the oxidizing agent. The compound that is reduced is the oxidizing agent. And then here, my carbon goes from plus 2 to plus 4. So it lost electrons. If it loses electrons, then it's oxidized. The compound that is oxidized is my reducing agent. So Fe2O3 is my oxidizing agent because it is reduced, and CO is the reducing agent because it is oxidized, okay? Let's do the same thing with this over here. So this is minus 2, so this will become plus 2. This is 0. Here, the nitrogen is, here this is minus 2. So minus 2 times 2, that's minus 4. So here this is plus 4. So look, pay attention. We don't care about this oxygen. This plus 2 turned into plus 4, so it lost electrons. This 0 turned into minus 2, so it gained electrons. The loss of electrons is oxidation, so this was oxidized. That means NO is my what? It's my reducing agent. Why? Because it was oxidized. Then O2, what happened to it? It gained electrons, so it was reduced. So O2 is my oxidizing agent because what happened to it? Because it was reduced, because it gained electrons. So now the last part would be part C. What does it say? We have FeSO4. It's Fe2 plus and SO4 2 minus. So you just do the crisscross method. So here you will get Fe is 2 plus and then SO4 2 minus. Here we need to actually do it. So S, it's going to be X plus 4 times minus 2 is equal to the total charge, which is minus 2. So I get X to be plus 6. So S is 6, oxygen is minus 2, okay? Then KMnO4. I know it's gonna be K plus and MnO4 to minus, so the K it's gonna be plus 1. The MnO4, sorry, not MnO4 to minus, just MnO4 minus. The MnO4 minus, we need to solve it, so let's solve it. So it's gonna be X plus 4 times minus 2 is equal to minus 1. You move this to the other side, I got X to be plus 7. So now this is plus 7 minus 2. 8H2SO4. Here you can do the crisscross method again. The hydrogen would get plus 1. The SO4, you just solve it as if it were SO4 to minus. So you will get that the sulfur is plus 6 and the oxygen is minus 2. Now here, you need to do the crisscross method again. So you get Fe3 plus and SO4 to minus. So now the Fe is 3 plus. My sulfur is SO4 to minus. So I solve it as if it were SO4 to minus. I get my sulfur to be plus 6 and my oxygen to be minus 2. Then I have MnSO4. MnSO4. So this is an ionic compound because it's a metal non-metal. It was Mn2 plus SO4 2 minus. So the Mn, it's plus 2, and then the SO4 2 minus, I'd solve it as if it were SO4 2 minus. So the sulfur is plus 6, and the O4, it's what? It's gonna be minus 2. Now the K2SO4, again, it's crisscross, so you should apply the crisscross method. You get K plus and SO4 2 minus. So the K has a charge or like an oxidation number of plus 1, and then of course SO4 2 minus, so plus 6 minus 2. And then finally H2O, the hydrogen has a charge of plus 1 and the oxygen has a charge or an oxidation number of minus 2. So I'm not going to explain to you how I did every single step. You should know by now. If you want to check, you can go open my other video. I'm sorry, but you should know by now, you know? So now let's cancel out the not needed parts, okay, or like the parts. Let's first of all focus on the parts that were oxidized and reduced. We have Fe. Fe, it was initially plus 2, it turned into plus 3. So Fe, it went from plus 2 to plus 3. That means it lost an electron. If it loses an electron, that means it's what? It's oxidized. If it's oxidized, then it's the reducing agent. SO4 2 minus, we don't care about it because it's everywhere. Okay, KMnO4. K was plus 1, it said plus 1, so we don't care about it. Mn, it was plus 7, it turned into plus 2. So, actually here you have to write the full compound. So here you will need to write KMnO4 it goes from +7 to +2, so it gains electrons. If it gains electrons, then it's reduced. If it's reduced, then it's the oxidizing agent, okay? Oxygen is -2 as usual. And then hydrogen, sulfur, okay, whatever, they don't really change. So these are the two main changes, and thus we got which one is the oxidizing agent and which one is the reducing agent. That's it for question number 8. And now finally, last but not least, the last and final question we have to solve is question 12, which is a disproportionation question. It's saying which of the following is a disproportionation question. What's a disproportionation question? Or what's a disproportionation reaction? It is in where a compound, it's not necessarily a compound, just the element in a compound is both oxidized and reduced, okay? So, a very famous example of a disproportionation reaction would be Cl2. What do I do to the Cl2? I add to it 2OH minus. What happens? The Cl2 will split into what? Will split into Cl minus, and it will give me ClO minus and H2O. So look what happened to the Cl2, which was originally 0. 1 chlorine, what happened to it? It got an oxidation number of -1, excuse me. And then this chlorine over here, okay, it's gonna be X. -2 is equal to -1. So it has an oxidation number of what? It has an oxidation number of +1. So my chlorine was both oxidized, meaning that it lost electrons, and reduced, meaning that it gained electrons. Okay, this is the definition of a disproportionation reaction. Now let's pay attention. SN2 plus, okay? Plus 2. 2Hg2 plus 2, 2Cl minus, -1. The +2 in the Sn turned into +4. This is the only change. It lost electrons, so it was oxidized. The +2 in the Hg stayed the +2. And then the -1 in the Cl, it turned into what? It turned into a -2. So in the first reaction, reaction A, there is no disproportionation reaction because nothing is both oxidized and reduced. Let's move on to part B. We have 3MnO4 2 minus, okay? MnO4 2 minus. X plus 2 times -2 is equal to -2. So X is going to be equal to what? Sorry, 4 times -2. So X is going to be equal to +6. So +6 minus 2 plus 1. Here, MnO4 2 minus. MnO4 minus, sorry. So that's going to be X plus 4 times -2 is equal to -1. So X, it's going to be equal to what? It's going to be equal to 8 minus 1, which is 7. So here +7. And then this is -2. And then MnO2. MnO2. X plus 2 times -2 is equal to 0. So then X, it's going to be equal to what? X, it's going to be equal to +4. So +4 minus 2. And then here this is going to be +1 and -2. Okay? So look at the Mn. This is the only thing on the reactant side that has Mn. It splits into Mn that has a charge of +7 and then Mn that has an oxidation number of +4. So the +6 got oxidized because it lost an electron, and it got reduced because it gained 2 electrons. So part B is a disproportionation reaction because the same element from a singular compound was both oxidized and reduced. Now part C, what does it say? 2NO plus O2 gives me 2NO, 2. So here this is +2 minus 2. This is 0. This is +4 minus 2. Here, this was oxidized. The oxygen here, we don't care about it, but this oxygen here, it was reduced. So, no, this is not a disproportionation reaction. That means the only disproportionation reaction I have is what is B. And that's it for the required questions for chemistry. Thank you guys for watching. I hope you enjoyed. I hope it was not too long of a video because I tried to fit everything that is required in, okay? If you want to watch the full chapter, I have completed for part A the full chapter of these videos. So anyways, thank you guys for watching. I hope you enjoyed and see you in the next video.